We are 24 co-creators away from the sleepy physicist, standing on solid ground. If you want to be one of them, link is in the description.
There is a kind of dark you can only find at a certain depth of night, when the room has been quiet long enough that even the ambient glow from the street has given up trying. Your hands disappear. Not dramatically, just gradually, the way attention loosens. You stop seeing the edges of things and you stop looking for them. And for a moment the darkness stops feeling like an absence and starts feeling like a texture. Something with mass. Something that has been there longer than the light. That sensation, if you're lying still enough to feel it, is a faint echo of something the universe once knew for a very long time. Lie here for a moment. There is no urgency. This is the sleepy physicist. And before we go anywhere, I want to say something quietly. If you are here regularly, if this is a place you return to, thank you. The steadiness of that, the returning, is what makes it possible to keep building. And if tonight is your first time, then welcome to a space that moves slowly on purpose. Before we go further, I want to take a moment to thank everyone who has chosen to support this channel on Patreon. You are the reason we are approaching 200 members, and every single person who joins moves the stability needle in a real and meaningful way. What I try to give back on Patreon is something I put thought into. There are stories of scientists, some whose names you will recognise, and some who have been almost completely forgotten by history. Some of those forgotten stories hit me in a way I did not expect. There are also detailed comparison documents where different objects and phenomena in space are laid out side by side, research notes for every video on this channel, and if you ever want to talk or have a topic you would like me to cover, you can reach me directly. The names of the top contributors are in the channel bio and on the founders page of the official website. We are eyeing 200 members, and that is the point where the sleepy physicist does not have to worry about its existence anymore. If you want to help us get there, the Patreon link is in the description. Now, let's go somewhere dark. Not the dark of your room, older than that. About 380,000 years after the Big Bang, the universe did something quiet and enormous. It cooled. Not in the dramatic way, no event you could have witnessed, no boundary you could have crossed. The temperature simply dropped over thousands of years, past a threshold. And when it did, the electrons that had been moving freely through the hot plasma finally slowed enough to be captured by protons. Hydrogen atoms formed. Whole ones, stib ones, and in forming they released the photons that had been scattering endlessly through that charged fog, released them all at once, in every direction, in a single uncoupling of light from matter. We can still detect those photons today. They are called the cosmic microwave background, and they carry in their temperature map every wrinkle and lean of the early universe, the seeds of everything that followed. But that is not what I want to sit with right now. What I want to sit with is what happened after the light left. After that uncoupling, the universe became, and this is the word I keep returning to, though I am not sure it fully covers it, quiet. The photons streamed away in all directions. The hydrogen and helium gas, now neutral, now transparent to radiation, settled. Gravity began its slow work on the density fluctuations that had been building since the first fractions of a second, and the universe entered a period that cosmologists call, with a plainness I find oddly moving, the Dark Ages. No stars, not one. The gas drifted. Gravity pulled it gently into the shallow wells that dark matter had already begun to carve. The temperature continued to fall, the universe expanded, and there was nothing to see because there was nothing producing light. Just hydrogen and helium, slowly thickening in places, thinning in others, falling toward densities that did not yet know they were falling towards something. This went on for a long time. How long is a number that the mind accepts without really absorbing? Somewhere between 100 million and 200 million years, though the exact figure is still a point of careful disagreement among people who spend their careers thinking about it. 100 million years of dark, cooling, drifting gas, the sun's entire lifespan, that figure, give or take, The Earth has not existed long enough to account for half of it. And during all of that time, the universe had no light source. None. The darkness was not a gap between events, it was the event. I sometimes think about what dark means in that context. It isn't the dark of a room or a cave or an unlit street. There was no surface for shadow to fall on. There were no eyes. Light existed, but those released photons were still travelling, but they were faint, cooling, already stretched by expansion toward wavelengths no human eye would register. For all practical purposes, for any physical observer that might have existed, which of course none did, the universe was dark, fully and everywhere and without exception. The gas, though, the gas was doing something. It was cooling below 200 Kelvin in certain places, thickening where dark matter had laid the earliest gravitational groundwork. Tiny fluctuations, density variations so small they seemed negligible, were being pulled together. Not quickly. Nothing about this was quick. But the architecture of what would eventually become the first stars was quietly assembling itself in the dark, the way ice begins forming in water that you cannot yet see freezing. Something was coming, the darkness didn't know it, the gas didn't know it, but the physics was already written, and the first light was waiting in it somewhere, patient as arithmetic. The first 3 minutes are the ones that get all the attention. And fair enough, a universe coup condensing from temperatures no laboratory has ever approached. Quarks assembling into protons and neutrons in the first seconds. The whole hot, dense mess of early spacetime doing something that no equation fully captures without approximation. It's a lot to put in 3 minutes. Physicists have spent careers on fractions of that opening window. But the thing the Big Bang left behind is less discussed. The residue, the specific inventory of what actually survived once things cooled enough to hold. Here is that inventory, roughly 76% hydrogen, about 24% helium, a trace, genuinely trace, parts per billion by mass, of lithium. And that was it. That was the entire chemical legacy of the first few minutes of existence. Not a starting point with room to grow, a hard ceiling, a sealed jar containing almost nothing, and the nothing inside it having a very specific composition that would shape everything that came after. No carbon, no oxygen, no nitrogen, no iron, no silicon, no calcium, no sulfur. None of the elements that make up the ground you walk on, the air you breathe, the biology that produces the thought you are currently having. None of it existed. Not in trace amounts, not hidden somewhere in the distribution, simply absent. The periodic table had 2 entries and a footnote. It's worth pausing on that, not because it's startling in a dramatic sense, but because the mind tends to treat it as a technical detail and move on. The absence of carbon is not a detail. It is, depending on how you look at it, the central fact of the early universe. Big Bang nucleosynthesis, the process that produced this inventory, had a window of roughly the first 20 minutes or so after the bang itself, when temperatures were hot enough for nuclear fusion, but the universe was expanding fast enough to prevent heavier elements from forming in significant quantities. Protons and neutrons fused into helium nuclei, some deuterium formed along the way and then largely converted, and lithium appeared in small amounts through a separate chain. Then the window closed. The universe cooled below the fusion threshold, and whatever had been made was what there was. The 76 to 24 split between hydrogen and helium isn't a coincidence or an approximation. It is a prediction, one that physicists calculated from first principles and that observations of ancient, barely enriched gas clouds have confirmed with a precision that is, honestly, a little unsettling. The universe in its earliest accessible state agrees with the theory. That agreement is one of the quieter triumphs of 20th century physics, the kind that doesn't get a press release because it confirms rather than surprises. What it means, though, the implications of that specific split, took longer to work out. The thing about hydrogen and helium is not just what they are, it's what they can't do. In a gas cloud collapsing under its own gravity, the ability to cool is everything. Cooling allows the cloud to shrink further. Shrinking raises the density. density increases the gravitational pull, and so on downward until a protostar forms. The rate at which a cloud can cool, the efficiency of the process, determines how much mass ends up concentrated in how few objects. Carbon cools gas beautifully. Oxygen cools gas. Iron, in its ionized states, radiates thermal energy with an efficiency that molecular hydrogen cannot approach. These elements cool gas through their electronic structure, through fine structure emission lines, through a dozen mechanisms that hydrogen and helium simply do not have at the temperatures relevant to star formation. They are, if you want to put it plainly, better at the job. In the early universe, none of them were available. The gas had only hydrogen, mostly in atomic form, some slowly assembling into molecules, and helium, which barely participates in cooling at all at low temperatures. No, actually, helium's contribution in these conditions is negligible enough that it almost doesn't belong in the sentence. What you had, for cooling purposes, was molecular hydrogen alone. And molecular hydrogen is slow. It has a cooling floor. Below about 200 Kelvin, it essentially stops radiating useful energy, stops pulling the temperature down, sits at the bottom of what it can do and goes no further. So the collapsing clouds of the early universe were warmer than ours, much warmer. And warmer clouds make larger stars, not by preference, not by accident, but by physics that connects temperature to mass through relationships that don't negotiate. The Big Bang left behind a universe that could only make a certain kind of star. What that star looked like is where this is going. Before the first star, before the first atom of hydrogen fell into the first point of density sufficient to matter, something else had already been working. Quietly, without light, without any signal that ordinary matter could detect or that any instrument of the time could have registered, because there were no instruments, no observers, no anything. Dark matter had been organizing itself along the contours of its own gravity for a long time. This is worth letting settle before moving forward. Dark matter does not interact with light. It does not emit, absorb, or scatter photons. In the period after recombination, when the newly freed photons of the cosmic microwave background were streaming away in all directions and ordinary matter was finally becoming neutral and cool, dark matter was already ahead of the process. It had been decoupled from radiation since much earlier, since the universe was too hot and dense for anything to hold a stable structure, and in that decoupling it had gained a kind of freedom that ordinary matter did not yet have. It could begin to clump. And it did. The density fluctuations in dark matter, the very slight over-densities that had been seeded in the first fractions of a second by quantum processes we still argue about, began to grow under their own gravity. Where there was slightly more, gravity pulled slightly harder. Where gravity pulled harder, more arrived. The overdense regions grew denser. The underdense regions thinned. Over millions of years, the dark matter distribution that had begun almost perfectly uniform developed structure. The way, no, actually the comparison I am reaching for might not quite work here. The way that a surface which appears flat will eventually reveal its topology when you watch water settle across it over a long time. What formed were halos, collections of dark matter held together by self-gravity, ranging enormously in mass from objects barely above what physics allowed to structures that would one day anchor entire galaxy clusters. The smallest stable halos that could form in this period, the ones relevant to the first stars, had masses in the range of roughly 100,000 to 1,000,000 times the mass of the Sun. These are called mini-halos. The name is accurate and somehow also insufficient. 1,000,000 solar masses sounds large until you consider that the Milky Way's dark matter halo contains something in the range of 1,000,000,000,000. A mini-halo is a small structure by cosmic standards, scattered, isolated, sitting in an expanding universe that was, in almost every direction around it, still nearly uniform gas. The ordinary matter, the hydrogen and helium left behind by nuclear synthesis, did not initially follow. It was still coupled to radiation pressure after recombination, still warm, still resistant to the kind of gravitational pull a mini-halo could exert. But the universe kept expanding and cooling, and as it did, the resistance eased. The baryonic gas began to respond. Slowly, over timescales of tens of millions of years, hydrogen and helium started to fall into the gravitational wells the dark matter had already dug. Fell is the right word, though it implies a speed that wasn't there. This was slow in the way that continents move, not perceptibly, not in any human timescale, but irreversibly. The gas descended into these pockets of dark matter, compressed slightly by the infall, and began to concentrate at the centre of each halo, where the gravitational potential was deepest. And here is where something interesting happens, or rather, here is where the conditions for something interesting began to accumulate. As the gas compressed at the centre of a mini-halo, it heated. Compression does that always. And as it heated, it needed to cool before it could collapse further, because thermal pressure pushes back against gravity, and without cooling the infall stalls. The gas needed to shed energy somehow, to lose enough heat to allow gravity to continue winning. This is where molecular hydrogen entered, and what it could and could not do will matter for a long time. But set that aside for now. The mini-halos themselves, these dark matter structures forming at redshifts somewhere between 20 and 30, meaning roughly 100 to 200 million years after the Big Bang, were not uniformly distributed. They were more common where the underlying density field was slightly higher, clustered in ways that reflected the original quantum fluctuations. They were isolated from each other, each one a small separate gravitational pocket. Not a galaxy, nothing like a galaxy. No disk, no arms, no stars already present to enrich the gas. Just dark matter and the hydrogen and helium falling toward its centre. These are where the first stars formed. Not in grand assembled structures, not in anything that resembled what we might intuitively think of as a birthplace. In pockets, small ones, spread across the dark of an early universe that had no other light sources and would not, for a while yet, develop any. Each mini-halo was an address. The universe's first luminous objects would be born at specific addresses, not in general. At particular concentrations of dark matter, at particular moments in the cooling history of a particular expanding space. That specificity seems important, though I'm not entirely sure why. Something about the idea that the first stars did not emerge from the universe in general, but from these small, cold, isolated pockets of it. That the darkness did not simply produce light everywhere at once. It produced it here, and here, and here. Each time in a place that had been quietly prepared by something no one can see, over a period of time no human nervous system is built to feel. To understand what the first stars became, you have to understand what the gas had to work with, and what it had to work with was almost nothing. One molecule, H2. Two hydrogen atoms bound together by a shared pair of electrons, forming the simplest molecular structure chemistry allows. In the present-day universe, molecular hydrogen is everywhere, in the cold cores of giant molecular clouds, in planetary atmospheres, in interstellar space between the spiral arms of galaxies. It is unremarkable in its abundance. But in the early universe, before the first stars had produced any carbon or oxygen or anything else, H2 was not merely common. It was the only thing available to cool a collapsing gas cloud. The only tool in a situation that required a very specific kind of work, and it was not quite built for the job. H2 does not form easily under primordial conditions. In the present-day interstellar medium, molecular hydrogen forms primarily on the surfaces of dust grains, tiny solid particles that act as meeting places where hydrogen atoms can land, find each other, bond, and release. Efficient, reliable, grain-assisted formation. In the early universe, there were no grains. There was no dust of any kind, because dust requires elements heavier than helium to exist, and those elements had not yet been made. Molecular hydrogen in primordial gas had to form through gas phase reactions alone, through a chain that begins with a hydrogen atom capturing a free electron to form H-, a negatively charged hydrogen ion, and then that H- reacting with another hydrogen atom to produce H2 and release the electron again. This works, but slowly, and the resulting abundance of H2 in a primordial gas cloud is low, on the order of 1 part in 1,000 or so, a thin fraction of the total gas. From that thin fraction, the cloud had to lose enough heat to collapse. Here is what molecular hydrogen can do. When a gas cloud contracts, the gas heats up, gravitational potential energy converts to thermal energy, and without some way to shed that heat, the thermal pressure builds until it pushes back against gravity, and the collapse stalls. H2 sheds heat by absorbing kinetic energy from collisions with other gas particles and re-radiating it as photons through rotational and vibrational transitions. When two hydrogen molecules collide and one of them gets bumped into a higher rotational or vibrational energy state, it eventually drops back down and releases a photon. That photon carries energy away. The gas loses a small amount of heat. And in a cloud with enough collisions happening across a long enough time, this can allow the temperature to fall and the collapse to continue. It is, and I want to be careful not to overdress this, it is a slow process doing heavy work. Something like pressing your palm to a barely warm radiator and waiting, genuinely waiting for the room to change temperature. The mechanism is real. The physics is correct. H2 cools primordial gas, but it does so at a rate and to a depth that has limits built into its structure. The limit that matters is around 200 Kelvin. Below that temperature, H2 begins to lose its ability to cool efficiently. The rotational transitions of the molecule require a minimum energy to excite, a threshold that the thermal collisions in the gas can no longer reliably meet, once temperatures fall below roughly 200 Kelvin. At that point, the molecule is still present, still technically capable of the transitions, but the collisions are no longer energetic enough to trigger them with any frequency. The cooling rate drops, the temperature floor arrives, and the gas sits there, unable to descend further, held at roughly 200 Kelvin by the physics of the molecule itself rather than by any external constraint. 200 Kelvin is not cold, not by the standards of what star-forming gas can reach. In present-day molecular clouds, the gas gets down to around 10 Kelvin, sometimes lower in the densest cores. This is possible because modern clouds contain metals, carbon, oxygen, silicon, iron in various ionized molecular forms, whose electronic and fine structure transitions are far more efficient at low temperatures than anything H2 can offer. Carbon monoxide alone, a molecule that requires carbon to exist, can cool gas to temperatures that H2 cannot touch. And dust, present in every modern star-forming region, adds yet another cooling channel at high densities, absorbing thermal energy from the gas and radiating it away in the infrared. None of that was available. The primordial cloud sat at 200 Kelvin and could go no further. That number, just 200 Kelvin, not an extreme value, not a dramatic constraint on its face, is the number that determined the minimum size of the first stars, because a warmer gas has higher thermal pressure. Higher thermal pressure means gravity needs more mass to overcome it. More mass required means the minimum collapsing unit is larger. The connection is direct. The math follows cleanly from temperature to mass, and the temperature was fixed by the cooling floor of a single molecule present in trace amounts, working through a mechanism that was the only option in a universe that had not yet made anything better. H2 did what it could. Given what it had to work with, that was not nothing, but it was not enough to make small stars. What it was enough for is the question that the next chapter begins to answer. Gravity is patient. It doesn't need to be fast. It applies its pull across whatever time is available and lets the physics handle the rest. But gravity also has opposition. A gas cloud, even one that is collapsing, even one where the inward pull clearly exceeds the outward pressure, pushes back. The gas is hot. Hot gas moves. Moving gas pushes against compression the way any pressured thing pushes against what is trying to contain it. This standoff between gravity and thermal pressure is not a struggle in any dramatic sense. It is just a competition between two quantities, and which one wins, and at what scale it wins, depends almost entirely on how hot the gas is. Let's stay with that. When a region of gas becomes dense enough that its own gravity starts to matter, there is a threshold. Below a certain mass, thermal pressure wins. The gas bounces back, the overdensity disperses, nothing forms. But at above that threshold, the point where gravity's pull on the accumulated mass finally exceeds what thermal pressure can resist, the collapse becomes self-reinforcing. The gas falls inward, compresses further, heats further, but if it can radiate that heat away fast enough, gravity keeps winning, and eventually you get a protostar. That threshold mass has a name, the Jeans mass. It is not a fixed number. It depends on the temperature and density of the gas, and the relationship with temperature is steep. The Jeans mass scales roughly as temperature to the power of 3/2, which means that if you double the temperature of the gas, the minimum collapsing mass doesn't double, it goes up by a factor closer to 3. The sensitivity is significant, and it runs in both directions. Lower the temperature, and the minimum collapsing mass falls sharply. Raise it, and suddenly only very large clumps can collapse at all. Press your palm slowly into a block of dense foam. The resistance you feel isn't rigid. It gives, but it doesn't disappear. Push with one finger and the foam holds. Push with your whole hand and the surface starts to yield. The threshold between holding and yielding is set by how firm the material is. Change the firmness and you change the threshold. That is what temperature does to a collapsing gas cloud. It sets the firmness of the opposition to gravity. In the present-day Milky Way and the molecular clouds where stars are forming right now, gas temperatures in the coldest star-forming cores reach around 10 Kelvin. At those temperatures, the Jeans mass comes out to roughly 1 to a few solar masses. This is why the Sun's mass is not a coincidence. It is roughly what you get when cold, metal-enriched gas collapses under gravity. It is the natural output of present-day conditions. In a primordial gas cloud, the temperature floor was around 200 Kelvin, not dramatically different on an absolute scale. 200 Kelvin versus 10 Kelvin, just 20 times warmer. But take that factor of 20 and raise it to the power of 3/2 and you get a Jeans mass that is not 20 times larger than the modern value. It is roughly a few hundred times larger, a few hundred solar masses. That is the minimum collapsing unit in primordial gas cooled only by molecular hydrogen. Not the typical size, the minimum. The floor below which gravity cannot yet win against the thermal pressure of gas sitting at 200 Kelvin. And this is, I want to be careful here because the number is doing a lot of work and it's easy to overstate what it means. This is not a soft estimate. The physics connecting temperature to Jeans mass has been confirmed across every star-forming region we can observe. The relationship holds. Changing the temperature changes the outcome, and changing the temperature by the amount that the absence of metal cooling forces on primordial gas changes the outcome by something in the range of 2 to 3 orders of magnitude. 200 Kelvin. That specific number, not a dramatic threshold, not the coldest thing or the hottest, just a floor set by a molecule's quantum mechanical structure, produced Jeans masses of hundreds of solar masses. Sitting with that feels to me like something other than coincidence. Not design, not intention, just a machine running that produces outputs you didn't necessarily expect from the inputs, and then the outputs compound. The primordial clouds that eventually began to collapse were not collapsing toward a star of a few solar masses, and then somehow growing beyond it. They were never going to collapse at that scale. The minimum collapsing unit was already enormous. The gas had no mechanism to reach the temperatures that would have allowed smaller things to form. This is why population 3 stars were not merely large by chance or by some localized condition in one particular region. They were large because the temperature was what it was, and the temperature was what it was because molecular hydrogen can only do so much, and molecular hydrogen was the only thing available. Each step follows from the one before it. The size of the first stars was not a property of those particular stars. It was a property of the universe they formed in. Look at any image of a star-forming region in the present-day universe, and what you see, if you know what you're looking at, is organized chaos. Not the poetic kind, the actual kind, where matter is doing many different things at many different scales simultaneously. In the Orion Molecular Cloud, which is the nearest large region of active star formation and has been photographed at every wavelength available to modern astronomy, there are hundreds of distinct dense cores, each one a separate gravitational collapse in progress, each one destined for a star of modest mass, the whole structure tangled and filamentary and producing new stars at scattered points across a volume several hundred light-years wide. This is what fragmentation looks like. A large cloud pulled by gravity into collapse, but also cooling rapidly and efficiently through the many channels available to metal-enriched gas. Carbon monoxide, water molecules, dust grains absorbing and re-radiating infrared. Cooling so well that as it contracts it can break. The gene's mass falls during the collapse because the temperature is falling, and as the gene's mass falls, subregions of the cloud that were previously too small to be gravitationally unstable suddenly become large enough to matter. They separate. They collapse on their own timescales. The big cloud becomes many small clouds, and the many small clouds become many small stars. This process, hierarchical fragmentation, is the reasons the present-day stellar mass function peaks near one solar mass. Not because there's anything special about one solar mass from the universe's perspective, but because the cooling physics of modern molecular clouds allows the gene's mass to fall far enough during collapse that solar mass clumps can separate and become gravitationally independent before the whole cloud finishes its infall. Primordial gas could not do this, and the reason it could not is the same reason the gene's mass was large to begin with. The cooling was too slow. Here is what happens in a collapsing primordial cloud. The gas begins to fall inward, driven by gravity in the mini-halo. As it compresses, it heats. The molecular hydrogen present in trace amounts, that 1 part in 1,000 fraction doing the only cooling work available, begins radiating, working against the temperature rise, trying to allow the collapse to continue. And it does allow the collapse to continue, at least initially. The temperature does not spike uncontrollably, but it does not fall either, not below 200 Kelvin, not ever, because that is where H2 stops being able to help. So the cloud contracts, it stays warm, and because it stays warm, the gene's mass stays large throughout the collapse. The subregions that would need to separate in order to fragment, in order for the cloud to break into smaller pieces the way a modern molecular cloud does, those subregions never become gravitationally unstable on their own. The gene's mass inside the collapsing cloud is always comparable to the total mass of the cloud itself, or not far below it. There is no internal scale at which a piece becomes independently self-gravitating before the whole thing arrives at the center. The cloud doesn't fragment, just falls. All of it, or nearly all of it, toward the densest point. The gas that should have been 100 separate protostars instead pours toward one, or at most a very small number, in the rare cases where the geometry or the turbulence creates some secondary concentration. One object at the center of a mini-halo, receiving the infall of an entire cloud's worth of hydrogen and helium, accumulating mass at a rate that modern star formation never approaches. I almost want to say the cloud refused to divide, which is not right. This isn't stubbornness, it's thermodynamics. But the physics has the texture of a refusal, something that should have happened, that happens everywhere in the modern universe, simply didn't. The cooling was not there to enable it, and so the mass that in a different epoch would have been distributed across dozens of stars stayed whole. What this meant for the forming star, the protostar sitting at the centre of that undivided infall, was not immediately obvious from the outside. It looked in simulation like a central condensation of gas growing denser and hotter as material arrived from all directions. The accretion rate was high, unusually high by the standards of anything forming today, because the infalling gas was warm and fast and plentiful and had nowhere else to go. The recent simulations, and I want to be honest that this picture has been refined since the earlier models, do show that disk fragmentation could occasionally produce a second or third object within the same halo, a companion forming from instabilities in the accretion disk around the primary protostar. So the phrase exactly 1 star per halo is probably too clean. But even in those cases the number of stars was small, 2, maybe 3, not hundreds, not the distributed population of a modern molecular cloud. The mass was still concentrated, still dominated by one large object receiving most of what the cloud had to give. A single drop of water hitting still water. The whole surface responding to one point of arrival, energy spreading outward from that single contact, everything organized around where the thing landed. Not shattered, not scattered, just absorbed, all of it, into the place where the mass decided to be. The gas fell, the protostar grew, and the scale of what it was becoming had already been determined, long before the nuclear reactions began, by the temperature at which the cloud had been stuck, and the inability of that temperature to fall any further. A protostar is not born at its final mass. It begins small, a dense knot of gas at the center of a collapsing cloud, hot enough to resist further compression temporarily, accumulating the material that continues to fall toward it from the surrounding envelope. The star it will become is not contained in that initial knot. It arrives later over time, carried inward by the gas that keeps falling after the central object has formed. This process is called accretion, and the rate at which it happens, how much mass arrives per year, per 1,000 years, across the full duration of the protostellar phase, is the number that determines the final mass of the star more than almost any other factor. That rate is set by the gas, specifically by how fast the gas is moving. The infall velocity of material collapsing toward a protostar depends on the thermal properties of the surrounding cloud, the temperature, the pressure, the sound speed of the gas, which is itself a function of temperature. In a warm cloud, gas moves faster. Faster moving gas falls inward faster. More mass arrives per unit time. The accretion rate scales with the cube of the sound speed, which means it is extremely sensitive to temperature. Steeper than a linear relationship, steeper than squared, the warmth of the gas is not a minor factor in the accretion rate. It dominates. Primordial gas sat at around 200 Kelvin. That is 20 times warmer than the 10 Kelvin cores of present-day molecular clouds where solar mass stars are forming right now. Take that factor of 20, apply the temperature dependence of the sound speed, and run it through the scaling for accretion rate, and you arrive at infall rates somewhere between 10 and 100 times higher than anything in the modern universe. A protostar forming in a present-day molecular cloud accretes at something like 10 to the power of minus 5 to 10 to the power of minus 6 solar masses per year, a slow-metered process that builds a star over hundreds of thousands of years, and can be interrupted at many points by the star's own feedback. A protostar forming in primordial gas was receiving material at rates closer to 10 to the power of minus 3 solar masses per year, sometimes higher. The difference is not dramatic in the way an explosion is dramatic. It is the difference between a surface where water moves reluctantly toward the drain and a surface where it doesn't even hesitate, where the whole geometry of the thing is organized around the center and everything moves toward it without detour. Real quick, I'm curious about something. What is the heat like where you are right now? I would love to know. Drop it in the comments. There is something worth sitting with in the list of things that were absent from the primordial accretion environment. No dust, because dust requires elements heavier than helium and none existed. No stellar winds from the forming star, because winds in massive stars are driven by radiation pressure on metal absorption lines, and there were no metal lines. No radiation pressure on dust grains in the infalling envelope. Again, no dust. No competing feedback from neighbouring stars, because in the isolated dark matter mini-halo there were no neighbouring stars. The list of things that normally interrupt or modulate accretion in modern star formation is long. Magnetic fields can couple to ionized gas and slow infall. Radiation from the protostar can heat the surrounding envelope and reduce the accretion rate. Jets and outflows can carry away angular momentum and material. Nearby massive stars can ionize and disperse the cloud before the forming star has finished accumulating its mass. In the primordial environment, most of these breaks either didn't exist or operated weakly. The gas fell, the protostar received it. The mass accumulated. What this produced, over timescales of a few thousand years, was a central object that had grown far beyond what any modern cloud would have allowed. A protostar that in a present-day molecular cloud would have gathered enough mass to trigger hydrogen fusion at around 1 solar mass, setting off the radiation that would slow and eventually halt further accretion, instead kept growing because the accretion rate was so high that the feedback from the forming star could not keep pace with the infall. This is, and I want to be careful not to overstate it, this is not a runaway process in the sense of having no physical limit. There were limits. The protostar's own radiation eventually mattered. The geometry of the halo set a ceiling on how much gas was available, and the timescale of the whole accretion phase was not infinite. But within those limits, the process ran harder and longer than anything that forms a star today. The protostar grew, kept growing, the gas arrived too fast for the feedback to answer it, and the object at the centre of the mini-halo, somewhere between a few thousand and a few tens of thousands of years into its formation, had accumulated tens, then hundreds of solar masses. Not because something exceptional happened, because nothing intervened. Set aside for a moment everything the previous chapters built toward, the cooling floors, the genes masses, the accretion rates, the absence of fragmentation. Set all of it aside and just ask the simplest version of the question, what did one of these things actually look like? What was it physically as an object? Start with the mass. A population 3 star, by the time it finished accreting and settled onto the main sequence, carried somewhere between roughly 100 and several hundred solar masses. Some models suggest the upper end reached higher, perhaps approaching 1,000 solar masses in the most extreme cases, though that figure carries more uncertainty than the lower range. But even the conservative estimate is worth pausing on. 100 solar masses. The Sun, which is itself a moderately large star by the standards of the present-day galaxy, contains 2 billion trillion kilograms of material. A population 3 star at 100 solar masses contained 100 times that. At 300 solar masses, 300 times. The radius did not scale the same way. These were not bloated, extended objects in proportion to their mass. They were, relative to their mass, compact. A star of 100 solar masses has a radius of perhaps 10 to 15 times the Sun's, not 100 times. The mass was there, but it was compressed, held in a tighter volume than you might expect. The internal pressure and temperature running at levels that the outer layers had to accommodate in a relatively small space. Dense with energy, not sprawling. The surface temperature is the number that shifts something in the understanding if you let it. The Sun's surface runs at about 5,778 Kelvin. That is hot enough to produce the yellow-white light we see, hot enough to cause sunburn through 150 million kilometers of space, hot enough that no material object could survive contact with it. Population 3 stars had surface temperatures near 100,000 Kelvin, 17 times hotter than the Sun, not warmer in the way one summer is warmer than another. A different category of heat, the kind that pushes against you from a distance the way the air near an open furnace pushes, before you're close enough for it to register as temperature, when it registers as pressure first. These stars were radiating at wavelengths the human eye cannot see, deep into the ultraviolet, flooding the space around them with photons energetic enough to strip electrons from hydrogen atoms across distances of tens of light years. And here is the thing that I keep returning to, because it seems, I'm not sure strange is the right word, but it's the one that arrives first. It seems strange that this temperature was essentially the same regardless of how massive the star was. Above roughly 40 solar masses, a population 3 star surface temperature converged on that same value near 100,000 Kelvin and stayed there. You could have a star of 100 solar masses and a star of 500 solar masses sitting side by side, and their surfaces would read almost identically on a thermometer. The luminosity would differ. The more massive star was dramatically brighter, but the surface temperature was locked. A machine that returns the same reading no matter how much material you feed into it. The physics of radiation pressure and opacity in metal-free stellar envelopes produce this convergence, and it is real, and confirmed by stellar models and still somehow odd to look at directly. The luminosity, though, that did scale, and it scaled steeply. These stars operated near what is called the Eddington limit, the point at which the outward radiation pressure from the star's luminosity balances the inward gravitational pull on its outer layers. For a star of 100 solar masses, the luminosity was something in the range of 1,000,000 times the Sun's output. 1,000,000 times. The Sun will, over the course of its entire main sequence lifetime, release an amount of energy that one of these objects released in a few thousand years. The photon output was not merely high, it was the dominant physical fact about the environment surrounding the star, shaping everything within tens of light years. No stellar winds carried material away from them. Modern massive stars lose significant fractions of their total mass over their lifetimes through radiation-driven winds, winds that require metal absorption lines to function, lines that population 3 stars simply did not have. The surface blazed at 100,000 Kelvin and poured ultraviolet radiation into the surrounding gas and produced essentially no outflow. The mass stayed. The star that formed was the star that died, approximately, without the gradual erosion that modern massive stars experience across their lifetimes. Blue-white, if you could be them, though the peak of their emission was far into the ultraviolet and what your eye would actually register, assuming you survived the radiation environment, which you would not, would be a white so intense it carried no information. Just light. Past the threshold where colour resolves into pure saturation. Hold that image for a moment, not as a visual, as a physical object. A few hundred solar masses of hydrogen and helium compressed into a volume perhaps 15 times the Sun's width, running at 100,000 Kelvin across its entire surface, pouring 1,000,000 times the Sun's energy output into the surrounding gas, retaining every gram of its mass because there was nothing to carry it away. This is what the early universe made. This is what the cooling floor of 200 Kelvin and the undivided infall of a primordial cloud and the high accretion rates of warm gas produced at the end of the process. Everything else in this story follows from it. There is a relationship between mass and lifespan in stars, and it runs exactly opposite to what intuition suggests. Larger stars do not live longer, they live shorter. Dramatically, disproportionately shorter, not in a linear way but in a steep, almost punishing curve, where doubling the mass cuts the lifespan by far more than half. The most massive stars in the present-day universe, objects of 50 or 100 solar masses, burn through their hydrogen fuel in a few million years. The Sun, at 1 solar mass, will spend roughly 10 billion years on the main sequence. A star of 1/10 of a solar mass may fuse hydrogen for trillions of years, longer than the current age of the universe by a factor of several hundred. The reason is not complicated once you see it. A star is a sustained nuclear reaction held in gravitational compression. The rate of that reaction is set by the temperature and pressure of the core, and the temperature and pressure of the core are set by how much weight the outer layers are pressing down on it. More mass means more weight pressing inward, means higher core temperature, means faster fusion. A massive star burns hotter and faster not because it chose to, but because the physics of pressure gives it no other option. And burning faster means exhausting the fuel sooner, regardless of how much fuel there was to begin with. The extra mass does not compensate for the extra rate. It never does. For population 3 stars, this relationship produced lifetimes of roughly 2 to 3 million years, largely independent of mass above about 40 solar masses. A star of 100 solar masses and a star of 300 solar masses arrived at approximately the same lifespan, because the higher luminosity of the more massive star consumed its proportionally larger fuel supply at a rate that cancelled most of the advantage. The clock ran at roughly the same speed for the whole upper range of the POP3 mass distribution, 2 to 3 million years. I find myself wanting to place that number somewhere I can feel it, and finding that I can't quite. The Sun has been burning for 4.6 billion years already. We are not halfway through its main sequence life. The Milky Way galaxy is approximately 13.6 billion years old. 2 million years, against those figures, is less than 2/10,000ths of the galaxy's current age. It is the kind of fraction that stops meaning anything when you write it down. Try it differently. The Sun orbits the centre of the Milky Way roughly once every 225 million years. In the entire lifespan of a population 3 star, from ignition to death, the Sun would not complete 1% of a single orbit. It would move through less than 1 degree of arc in its 360-degree circuit around the galaxy. The stars that built the universe lived and died in the time it takes the Sun to cross a single arm. There is a specific sensation that comes from watching a candle you know is nearly finished. The flame itself looks the same as it did an hour ago. The light is identical, but the wax is almost gone, and you are aware of that in a way that changes how the light feels, even though the light hasn't changed. The awareness of remaining time is not in the flame, it is in you. Population 3 stars had no such awareness. They burned at full luminosity from roughly the first moments of hydrogen fusion to the last. 1 million solar masses of light output poured into the surrounding gas at the same rate on the final day as on the first. The surface temperature unchanged, the ultraviolet flood undiminished, right up until the hydrogen in the core ran out. And then something changed very quickly. When the hydrogen in the core is exhausted, the nuclear burning that has been providing outward pressure against gravitational compression suddenly stops. The core, no longer supported, begins to contract. This contraction heats the core further, enough in a sufficiently massive star to begin burning helium and later heavier elements in successive shells. The star's outer layers respond to the changing pressure balance by expanding. The structure of the star changes, and the clock that has been running since ignition reaches its final minutes. For a population 3 star, those final minutes, stretched across thousands of years of stellar evolution, but compressed into almost nothing by the timescales we've been discussing, led somewhere specific, determined by mass, producing outcomes that the universe had never seen before. 2 to 3 million years, gone. What came next is where the early universe changed permanently. Modern massive stars do not die at their birth mass. They arrive at death lighter, sometimes significantly lighter, than the objects they were when they first settled onto the main sequence. The difference is carried away by wind. Stellar winds are not a metaphor. They are a physical outflow of material from a star's surface, continuous across the star's lifetime, driven by the pressure of the star's own radiation pushing outward against its outer layers. In sufficiently massive stars, this outflow is substantial. A star of 60 or 80 solar masses in the present-day universe may lose 20, 30, sometimes 40 solar masses or more across its main sequence lifetime, material streaming away from the surface, expanding outward into the surrounding gas, never returning. What remains at the end is a star considerably less massive than the one that formed. The mechanism that drives this requires a specific ingredient. When photons stream outward from a star's interior, they carry momentum. As they pass through the stellar atmosphere, they can transfer that momentum to the gas, pushing the outer layers outward, contributing to the overall radiation pressure. But the efficiency of this transfer depends on how readily the gas absorbs the photons, and that depends on what the gas contains. Metal ions, iron, carbon, oxygen, silicon in various ionization states, absorb photons at specific wavelengths corresponding to their electronic transition energies. These absorption lines are, in a sense, handles. The photon pushes on the ion carries the momentum, and the ion carries it outward, dragging gas along with it. In metal-rich stellar atmospheres, these handles are numerous. The photons have many opportunities to transfer momentum. The wind is driven efficiently and continuously across the star's entire surface. Population 3 stars had no metal lines. Not few, none. Their atmospheres were hydrogen and helium, which have far fewer and less efficient absorption features at the relevant temperatures. The photons streamed outward through the atmosphere and found very little to push against. The momentum transfer was negligible. The wind that should have been there, The steady outflow that would have been stripping mass across millions of years was essentially absent. A sealed bottle dropped into the water takes on no water. The pressure outside is real and the pressure inside is real, and the bottle sits between them unchanged because the boundary holds. A population 3 star sat inside its own radiation field for 2 to 3 million years and lost almost nothing to it. Not because the radiation wasn't there, it was in enormous quantities, but because there was nothing in the atmosphere for it to grip. This had a consequence that is difficult to fully appreciate until you think about what death means for these objects. The final mass of a star, the mass it carries into the last phase of its evolution, when the core runs out of fuel and the structure begins to change, determines almost everything about how it ends. The death pathways available to a massive star, the thresholds between different outcomes, are mass-dependent. Whether a star produces a particular kind of supernova, whether it collapses to a neutron star or a black hole, whether the explosion succeeds in disrupting the whole star or falls back onto the remnant, these questions are answered by the mass at the moment of death. For modern massive stars, that mass is substantially lower than the birth mass, because wind has been working on it for millions of years. The death mass is the birth mass minus everything the wind took. For population 3 stars, the death mass and the birth mass were approximately the same thing. Whatever mass the star had accumulated by the end of its accretion phase, 100 solar masses, 200 of 300, it carried that mass, essentially intact through its entire main sequence lifetime and into the final reckoning. Nothing had been shed, nothing had escaped. The star that died was the star that formed, complete, undiminished in mass, arriving at the moment of core collapse or pair instability or direct black hole formation as fully massive as it had ever been. There is something about this that feels, I want to be careful here, not tragic exactly, but complete in a way that amplifies what came next. A modern massive star at least sheds some of itself before the end. The wind disperses material gently, gradually, giving something back to the surrounding gas across the star's lifetime. Population 3 stars gave nothing back until the very last moment. And when that moment arrived, what was released was the entire accumulated mass of an object that had been building for thousands of years and holding everything for millions. The implications of that completeness are where the next chapters live. There was a moment, not dramatic in the way the word implies, not announced, not preceded by any signal that it was coming, when the universe contained a star for the first time. Before that moment, for somewhere between 100 and 200 million years, depending on which models you trust and how precisely you define the beginning of what we are discussing, there had been nothing producing light from nuclear fusion. The photons released at recombination were still travelling, still crossing the expanding universe in every direction, already stretched by expansion into microwave wavelengths, faint and cooling and carrying the imprint of the early density field in their temperature variations. But those were relic photons, light from an earlier state of things, not stellar light, not the kind of light that comes from a sustained nuclear reaction inside a gravitational object, from hydrogen fusing to helium in a core hot enough to hold that process indefinitely. Stellar light was new, the first star, wherever it was, whichever mini-halo it formed in at whatever precise moment in that slow drift between 100 and 200 million years post-Big Bang the conditions finally aligned, ignited hydrogen fusion in its core and began pouring photons into the surrounding gas. The photons left the stellar surface at roughly 100,000 Kelvin, peaked deep in the ultraviolet, and began crossing the primordial gas that surrounded the mini-halo. And what happened next was not what we might loosely imagine as light entering darkness and illuminating it. What happened was physical, chemical almost. The ultraviolet photons from that first star carried enough energy, above 13.6 electron volts per photon, to strip electrons from neutral hydrogen atoms. This is the ionization energy of hydrogen, the minimum required to knock a bound electron free, and the population 3 stellar spectrum produced these photons in numbers that no later generation of stars would match per unit of stellar mass. As the photons moved outward from the stellar surface and encountered the surrounding neutral hydrogen gas, they ionized it. The hydrogen atoms absorbed the photons and released their electrons. The gas changed state from neutral to ionized, from transparent at some wavelengths to opaque at others, from a passive medium to something actively interacting with the radiation passing through it. The region of ionized gas surrounding the star is called an H2 region. Every massive star in the present-day universe produces one, but the first one was, in a quiet and uncelebrated categorical sense, the first one, the first volume of gas in the history of the universe to be ionized by stellar irradiation, a sphere of restructured matter expanding outward from the first star at a rate set by the balance between the ionizing photon output and the density of the surrounding neutral gas. It expanded slowly by the standards of things that move quickly. Slowly is the right word, and I want to hold it there rather than replace it with something that implies more drama. The HII region around a single population 3 star grew at a rate determined by how fast the star could ionize the gas at its expanding edge, balanced against the rate at which ionized hydrogen was recombining back to neutral. The recombination rate depends on density, and the primordial gas in and around the Minihalo was dense enough that the expansion of the HII region was not instantaneous. It took time. The boundary between ionized and neutral gas, a transition that would eventually, given enough stars and enough time, encompass the entire universe, began as a small specific thing surrounding one object in one mini-halo somewhere in an otherwise dark and neutral cosmos. And then the second star formed, and the third, in other mini-halos scattered across the universe, in no particular order, with no coordination, each one igniting its own surrounding HII region, each one adding its photon output to a universe that was, for the first time, producing competing sources of light. Whether a single star could have produced a detectable effect on the intergalactic medium is something that depends on how you define detectable. Probably not. The universe was large and the star was one. But the ionized region around it was real, and it was doing something to the gas that no physical process had done before, and the physics that it set in motion was the same physics that would eventually, over hundreds of millions of years more, complete the reionization of the entire intergalactic medium. Something was beginning, not loudly, not all at once. The way light enters a room that has been dark for a long time, not in a flood but along surfaces, along edges, the shape of the room returning gradually as the dark retreats, rather than disappearing. This is closer to how the universe's transition from neutral to ionized proceeded. Slowly at first, in small pockets, in isolated regions around isolated stars, then more, as the population of Pop 3 stars grew, then more still, as the first galaxies assembled and their collective light output became something the intergalactic medium could no longer absorb. But all of that came later. At the start, there was just the one star in its mini-halo, producing the first ultraviolet photons that had ever come from hydrogen fusion in the history of the universe, and the boundary of its H2 region moving outward through neutral gas that had been waiting, in no meaningful sense but in a physically real one, for a very long time. What that process became at scale is the next chapter. The number that keeps appearing in discussions of population 3 stars and reionization is this: up to 30 times more ionizing photons per unit of stellar mass than the generation of stars that came after them. 30 times. It is a ratio that deserves a moment before it gets buried in the mechanism it produces. A population 2 star, a star with some metallicity, cooler than its primordial predecessors, forming in gas already touched by the first supernova, produces ionizing photons certainly. All sufficiently massive stars do. But the surface temperature of a population 3 star near 100,000 Kelvin placed the peak of its emission deep into the ultraviolet, into photon energies that ionize hydrogen, with far greater efficiency than the output of a cooler stellar surface. The photon yield per baryon of stellar material was not modestly higher. It was, in the range of models that best fit the available constraints, an order of magnitude or more above what population 2 stars contributed per unit mass. This mattered because reionization required an enormous number of photons. Every hydrogen atom in the intergalactic medium, and the intergalactic medium at the relevant epoch, was essentially all hydrogen and needed to absorb at least one photon above 13.6 electron volts to become ionized. And then it needed to stay ionized, which meant the ionizing photon supply had to outpace the rate at which free electrons and protons were recombining back into neutral hydrogen. Recombination was happening continuously. It still happens continuously wherever ionized gas exists. The balance between ionization and recombination is not a one-time transaction, but an ongoing competition, and winning it, keeping the universe ionized, required a sustained photon output across hundreds of millions of years. The population of population 3 stars distributed across the mini-halos of the early universe was producing that output, not from a single concentrated source, from many thousands of individual stellar objects, each surrounded by its own expanding HRIY region, each pouring ultraviolet photons into the surrounding gas at a rate that no later stellar generation would match per unit of mass. The H2 regions grew, each one expanding outward from its central star at a rate set by the ionizing photon flux and the local gas density, each one a sphere, roughly speaking not perfectly, of ionized hydrogen surrounding a point of light in an otherwise neutral universe. Cosmic reionization is the name given to the process by which these spheres eventually grew large enough and numerous enough to overlap, to merge, to dissolve their boundaries into one another, until the ionized regions were no longer isolated pockets but a connected, interwoven medium covering the intergalactic volume. That name, cosmic reionization, is one of those labels that implies a tidiness the actual process didn't have. It sounds like a phase transition, a moment. It wasn't. It was uneven, overlapping, proceeding at different rates in different regions depending on the local density of ionizing sources, the local density of gas, and the history of star formation in each patch of the universe. Regions nearer concentrations of early star-forming mini-halos ionized first. Underdense regions with fewer sources lagged behind. The boundary between ionized and neutral was not a clean front advancing uniformly across the universe, but something more like, and I am almost reluctant to reach for this comparison because it doesn't quite carry the scale, something more like fog thinning in patches, visibility opening here before there, the transparency arriving not as a wave, but as an accumulation of local clearings that eventually ran together. The process began with the first POP3 stars and extended, by most estimates, until roughly 1 billion years after the Big Bang, at which point the intergalactic medium was largely ionized and the universe had become transparent to ultraviolet light in the way we observe it to be today. That is a duration of several 100 million years, give or take the significant uncertainties that remain in constraining when reionization completed. Several 100 million years of continuous overlapping ionization, a slow tide rising in isolated pockets until the pockets were no longer isolated. What the universe looked like partway through this process is something that observational cosmology is only beginning to access. The cosmic microwave background carries a statistical imprint of the reionization epoch in the polarization of its photons, scattered by the newly freed electrons that reionization produced. Quasar spectra at high redshift show the Gunn-Peterson trough, a signature of neutral hydrogen absorbing the quasar's ultraviolet light along the line of sight, fading out as the universe becomes more ionized toward lower redshifts. These are indirect measurements, fossils of the process, rather than images of it. What can be said is that the universe accessible to us now, transparent, allowing light to travel billions of light years without being absorbed by neutral gas, permitting the observations that built all of modern cosmology, is the downstream result of reionization. And reionization began with population 3 stars, with their surface temperatures near 100,000 Kelvin and their photon outputs 30 times higher per baryon than what came after. They were the first agents of a process that changed the physical state of the entire intergalactic medium. Not quickly, not all at once, but they started it. By the time the last population 3 stars were dying, and they were dying on timescales of only a few million years, remember, already gone before the process they initiated was anywhere near complete, the universe they were leaving behind was already different from the one they had been born into, not transparent yet, not finished, but changed in a direction it would not reverse. The fog was thinning, slowly, unevenly in patches, but it was thinning. Mass determines almost everything about a star's life. It sets the core temperature, the fusion rate, the luminosity, the lifespan. But mass at the moment of death is the number that matters most in a different sense. Not for what the star experienced while living, but for what it left behind. And for population 3 stars, which arrived at death carrying essentially the same mass they were born with, this number sorted them into 3 completely different endings. Not variations on a theme. 3 distinct physical outcomes, each one producing a different kind of object, or no object at all, and each one having different consequences for the gas around it, for the metals released or not released, for the black holes seeded or not seeded, for the universe downstream, the lowest mass range first. Stars in roughly the 10 to 40 solar mass window, modest by population 3 standards, but still far larger than anything forming in the present-day galaxy with any frequency, ended in core collapse supernovae. When the hydrogen in the core was exhausted, the star moved through successive burning stages, fusing heavier elements in a series of shells around an iron core that grew until it could no longer support itself. Iron does not release energy when fused, it absorbs it, and so when the iron core exceeded a critical mass, the pressure support disappeared. The core collapsed in less than a second, bouncing at nuclear densities and driving an outward shockwave through the infalling outer layers. The result was an explosion, a neutron star or small black hole at the center, and an expanding shell of gas and newly synthesized heavy elements moving outward into the surrounding medium. These were, in some ways, the most familiar deaths. Not unlike what happens to massive stars today, adjusted for the different composition and the absence of metal-driven mass loss across the preceding lifetime. The second pathway is the one that requires the most pause. Stars between roughly 140 and 260 solar masses, a range that sits comfortably within the upper portion of what population 3 formation models predict as typical, faced a death mechanism that has no analogue in the present-day universe, at least not one that has been confirmed observationally. At this mass range, the core temperatures reached during the late stages of stellar evolution became high enough, and the core densities low enough for a specific quantum process to occur, the spontaneous production of electron-positron pairs from the collision of high-energy photons. This matters because photons provide radiation pressure, and radiation pressure is part of what holds a massive stellar core against gravitational collapse. When photon energy is converted into matter, into electron-positron pairs, the radiation pressure drops. The core loses support. It begins to contract. But the contraction heats the core further, which accelerates the nuclear burning, which releases energy faster than the collapse can absorb it. The result is a thermonuclear explosion of the entire star, not just the outer layers, not just a shell, but the complete disruption of the object from core to surface. This is a pair instability supernova. The star does not leave a neutron star, it does not leave a black hole. It leaves nothing but an expanding cloud of gas and the heavy elements produced in the explosion. The entire mass of a star that might have been 200 solar masses is returned to the interstellar medium at once. If you're finding this interesting, consider leaving a like and subscribing. It genuinely helps more people find their way to content like this. The third pathway is the quietest, and in some ways the strangest to sit with. Stars below roughly 40 solar masses in the POP3 range, and stars above roughly 260 solar masses did not explode at all, or at least not in a way that left anything behind to expand outward into the surrounding medium. In the lower portion of this range, The supernova shock failed to overcome the ram pressure of the infalling envelope, and the matter fell back onto the compact remnant. In the upper range, the very most massive population 3 stars, those above 260 solar masses, the core collapse proceeded so rapidly, and the gravitational binding energy was so large, that the explosion could not unbind the star. The whole object fell inward, a star of 300 solar masses, there and then not there. No outward shock, no dispersed heavy elements, no neutron star spinning at the center of an expanding remnant, just a black hole at the location where the star had been, carrying the mass of the star inward without ceremony, without visible release. The path through these 3 outcomes was set entirely by mass. Take the same species of object, a population 3 star, formed from pristine hydrogen and helium in a dark matter mini-halo, and give it 30 solar masses, and it ends in core collapse and a neutron star. Give it 200 solar masses, and it ends in a total thermonuclear disruption that seeds the surrounding gas with oxygen and silicon and calcium. Give it 300 solar masses, and it ends in silence. Same origin, same composition, same formation. Physics, 3 different forks in the path, each one leading somewhere the others do not go. What each fork produced for the universe it left behind is where the next chapters go. For most of its life, a massive star exists in a state of negotiated balance. The core is hot enough and dense enough to sustain nuclear fusion, and the energy released by that fusion pushes outward against the weight of everything above it. The outer layers press inward. The radiation pressure pushes back. These 2 forces have been holding each other in place for millions of years. By the time a population 3 star in the 140 to 260 solar mass range reaches the end of its hydrogen supply and begins the sequence that ends in the most energetic thermonuclear event the universe produces. The sequence begins quietly, as these things tend to. After the hydrogen in the core is exhausted, the core contracts under gravity and heats. Helium burning begins, producing carbon and oxygen. The carbon and oxygen accumulate as the helium is consumed. In a star of sufficient mass, the temperature in the contracting carbon-oxygen core eventually climbs past a threshold that lower mass stars never reach. Somewhere around 4 billion Kelvin, at densities low enough that the electrons in the gas are relativistic, but the core has not yet become degenerate in the way that lower mass cores do. At this temperature and this density, something begins to happen that has no precedent in the earlier life of the star. High-energy photons, gamma rays produced by the thermal radiation of the core at these extreme temperatures, begin spontaneously converting into electron-positron pairs. This is not a chemical reaction. It is a quantum process, the materialization of matter and antimatter from the energy of light, permitted by special relativity when photon energies exceed the combined rest mass energy of an electron and a positron. The process requires specific conditions, high temperature, relatively low density, and a star between 140 and 260 solar masses at the end of its helium-burning phase provides exactly those conditions in its core. The problem for the star is what this does to the pressure. Radiation pressure in a stellar core is carried by photons. When those photons are converted into electron-positron pairs, into mass rather than radiation, the number of photons carrying pressure decreases. The radiation pressure drops. And radiation pressure, in a massive stellar core operating at these temperatures, is not a minor contribution to the total pressure support. It is substantial. Its sudden reduction is, and this is where I want to be careful about what word to use, because the standard ones don't quite cover it. It is like a floor that has been holding weight for millions of years, discovering in a fraction of a second that it no longer has the structural integrity to continue. Not cracking, not bending, simply ceasing to hold. The core begins to collapse, but the collapse immediately heats the core further because gravitational potential energy converts to thermal energy as the gas compresses, and this heating accelerates the nuclear burning. The carbon and oxygen that have been accumulating begin fusing explosively, releasing energy at a rate that the controlled burning of the main sequence never approached. The burning does not proceed in an orderly way, it proceeds in a runaway, the heating driving faster burning, the faster burning releasing more energy, the energy having nowhere to go because the collapse was supposed to be the pressure release, but the burning is now releasing more energy than the collapse is consuming. The energy wins. The outward pressure from the explosive nuclear burning reverses the collapse before the core reaches densities that would produce a neutron star or a black hole. The infall stalls. Then it reverses. A shock wave drives outward through the stellar interior, expanding into the layers above the core, carrying with it the energy of an explosive event that has lasted from the beginning of the pair production instability to the reversal of the collapse somewhere on the order of seconds. Seconds. A star that has been in existence for 2 to 3 million years encounters the pair instability threshold and resolves it in seconds. The shockwave moves outward through the star at a significant fraction of the speed of light in the stellar interior, heating and accelerating the material it passes through, carrying more than 10 to the power of 44 joules of energy, an amount that is, in practical terms, not meaningfully comparable to anything in ordinary experience. Several times the total energy output of the Sun across its entire 10 billion year lifespan, released in the time it takes the shockwave to cross the stellar radius. The outer layers of the star accelerate outward. The entire structure of the star, the core that held the pair instability event, the helium shell above it, the hydrogen envelope above that, is disrupted. Not partially. There is no remnant. The explosion does not leave a neutron star spinning at its center, does not leave a black hole accreting the infalling material that the shock didn't reach. The energy is sufficient to unbind every layer of the star from every other layer, to convert what was a gravitationally bound object into an expanding shell of gas, carrying the full nucleosynthetic yield of the star's lifetime. This is the part that I keep returning to. A pair instability supernova leaves nothing behind. Other supernovae leave compact remnants, objects you can point a telescope at, spinning pulsars or accreting black holes embedded in expanding nebulae. A pair instability supernova leaves a location, a place in space where a star was, now occupied by gas moving outward at thousands of kilometers per second and nothing else. No center, no remnant, no object, just the products of millions of years of nuclear burning released all at once into the surrounding medium. Oxygen, silicon, sulfur, calcium, the heavy elements that the early universe had never contained until these stars made them, and these explosions released them. Expanding outward, into a universe that had never held them before. Before the first pair instability supernova, the universe had been running for somewhere between 150 and 300 million years. The estimates vary depending on when exactly the first massive stars formed and how long they took to exhaust their fuel. And in all of that time, in every direction across every volume of space, there was no free oxygen, no silicon, no sulfur, no calcium, no carbon moving through the interstellar medium. The periodic table existed as a concept waiting for the physics to fill it in, but the physics had only gotten as far as hydrogen and helium and a trace of lithium before the conditions for building further became unavailable. The first stars built further. Inside a population 3 star on the main sequence, the core was fusing hydrogen into helium at temperatures and pressures that produced helium nuclei, alpha particles, in enormous quantities. This is where the process began, not dramatically but steadily. The same reaction that powers the Sun and repeated at a rate scale to the much higher core temperatures and pressures of an object 10 or 100 times the Sun's mass. Hydrogen burned, helium accumulated, the core composition changed slowly across the star's brief lifetime until the hydrogen was gone and the helium dominated. Then the core contracted and heated further, and helium began to fuse. Helium fusion, the triple alpha process, is one of the more improbable reactions in stellar physics. 3 helium nuclei must combine to form carbon-12, and the intermediate step involves beryllium-8, which is unstable and decays in approximately 10 to the power of minus 16 seconds. The reaction only proceeds because carbon-12 has a resonance energy level that makes the final step slightly favoured A coincidence of nuclear structure that was noticed by Fred Hoyle and confirmed experimentally, and which he took as evidence. Controversial evidence. And I should be clear that the mainstream of physics does not share his later conclusions, that the universe was somehow arranged for carbon's existence. The nuclear physics is real, the interpretation is separate. Carbon formed. And once carbon existed in the core, further reactions became possible. Carbon nuclei captured additional alpha particles and built oxygen. Oxygen built neon. Neon built magnesium. The sequence continued upward through the periodic table in successive burning stages, each one requiring higher temperatures than the last, each one proceeding faster as the star neared its end. Helium burning taking thousands of years, carbon burning taking centuries, neon burning taking perhaps a year, oxygen burning taking months, silicon burning taking days. Silicon burning is where the chain reached iron and stopped, for the stars in the lower POP3 mass range. For the pair instability stars, the sequence reached a different kind of stopping point, not the iron peak, but the instability threshold, where the temperature and density conditions triggered pair production before the silicon could fully burn to iron, and the explosion that followed dispersed the nucleosynthetic products of everything that had come before it. Roughly 100 solar masses of processed material ejected outward. Oxygen was the largest component by mass. A pair instability supernova from a population 3 star in the 150 to 250 solar mass range produced oxygen in quantities that dwarf the output of standard core collapse, supernovae. Oxygen is, and this is the part I keep returning to, quietly without quite knowing why, oxygen is already the most abundant element in the Earth's crust, in the oceans, in the human body by mass. It exists everywhere in the present-day universe in the molecular and ionic forms that chemistry requires for complexity. And the first free oxygen in the history of the universe came from events like this one, ejected from stars that had never been observed and will never be observed directly. In the surrounding gas, the already abundant hydrogen was waiting. Oxygen and hydrogen. The combination that produces water under the right pressure and temperature conditions. Nothing arranged this. The hydrogen was there because nucleosynthesis left it there. The oxygen arrived because a star between 140 and 260 solar masses hit the pair instability threshold and disrupted itself. The eventual production of water was a downstream consequence of those two unrelated facts existing in proximity across the billions of years it took for the oxygen to mix into the interstellar medium, collapse into new gas clouds, and find itself in a planetary system with enough hydrogen to combine with. Silicon came out of the explosion too. Silicon is what rock is largely made of, the backbone of the Earth's mantle, the material in the grains of sand that exists in enormous quantities on a planet that would not exist without silicon having been produced somewhere. Sulfur, calcium, the element in bone, in shells, in the carbonate structures of marine organisms that would not appear for billions of years after this explosion, but would, when they did, draw on calcium that traced its origin to something like this moment. The supernova expanded outward. The heavy elements it carried moved into the surrounding neutral gas of the mini-halo, then beyond, mixing slowly with the intergalactic medium, spreading across distances that took light thousands of years to cross. The seal had given way. What had been locked inside the gravitational compression of a stellar core for 2 to 3 million years was now outside it, irreversibly, moving through a universe that had never contained these atoms before, and would now always contain them. Something had changed that could not be unchanged. The universe that existed after this explosion was not the same as the one before it, not dramatically different, not immediately transformed, but different in a chemical sense that would compound over billions of years into a universe with planets, with water, with the slow molecular machinery that eventually produces something capable of asking where any of this came from. The first metals were out, and what they did to the gas they entered is the next chapter. The gas that surrounded the first pair instability supernovae was, before the explosion, the same gas that had always been there. Hydrogen and helium in the same proportions that nucleosynthesis had fixed 3 minutes after the Big Bang, sitting in the mini-halo and the intergalactic medium beyond it, governed by the same cooling physics that had shaped every collapse since the Dark Ages ended. Molecular hydrogen doing what it could. The temperature floor at 200 Kelvin. The gene's mass sitting at hundreds of solar masses. The same conditions producing the same kind of objects in the same way. Then the ejector arrived. Not quickly, the expanding shell of a pair instability supernova moved outward at thousands of kilometers per second, which sounds fast and is fast by any human measure. But the distances involved in mixing heavy elements through a mini-halo and into the surrounding intergalactic medium are large enough that the process took thousands of years at minimum and tens of millions of years before the enriched gas had spread and mixed to the point where the next generation of star formation could sample it. The metals moved through the surrounding gas slowly, in the way that something dropped into still water spreads, not instantly, not uniformly, but irreversibly. As the heavy elements mixed into the gas, they changed what the gas could do. The mechanism is not complicated, once you know what to look for. Carbon and oxygen, in their ionized and molecular forms, have the electronic transition energies that fall in ranges where the thermal emission of a cooling gas can excite them efficiently at temperatures well below 200 Kelvin. Carbon, in particular, has a fine structure emission line at 158 microns, a specific wavelength at which ionized carbon radiates thermal energy away from the gas with an efficiency that molecular hydrogen cannot match at those temperatures. Oxygen contributes its own fine structure lines. Together, these elements opened cooling channels that had not existed before, pathways by which the gas could continue losing energy below the 200 Kelvin floor that had previously been the end of the road. The floor moved, and here is where I want to slow down, because the number involved is easy to pass over. The critical metallicity, the threshold above which this new cooling becomes efficient enough to change the fragmentation behavior of collapsing clouds, is approximately 10 to the power of -5 solar metallicity, 100,000th of the metal content of the Sun. A contamination so small it would be difficult to detect directly in a gas cloud if you weren't looking for it carefully. A quantity that sounds like nothing. The kind of fraction that appears in the notation of chemistry when you are describing trace amounts. Impurities, something present but barely. That was enough. At that concentration, the new cooling channels became operational during the cloud collapse, in a way that changed the thermodynamics of the infall. The gas that had previously been stuck at 200 Kelvin could now continue cooling. It pushed past 100 Kelvin, past 50, down towards the temperatures that present-day molecular clouds reach routinely. And as the temperature fell, the gene's mass fell with it, steeply because of the c to the power of 3/2 scaling that had worked against primordial star formation and now worked in the other direction. Where the gene's mass had been hundreds of solar masses, it dropped to tens, then to a few, then in the coldest and densest cores of these newly enriched collapsing clouds, to something approaching 1 solar mass. The door was, and I keep reaching for this image, though I want to be careful not to dress it up more than it deserves. The door was not thrown open. It was simply found to be open when the gas arrived at it. The cooling physics changed, the fragmentation scale changed, and the universe that had been producing only objects of hundreds of solar masses was now producing something smaller, for the first time in those regions where the metals had reached sufficient concentration. The collapsing cloud that would previously have poured its entire mass into 1 or 2 massive objects instead began to develop substructure. Density fluctuations within the infalling gas, fluctuations that had always been there but had previously been too small relative to the gene's mass to become gravitationally independent, became large enough to matter. They separated. They collapsed on their own. The cloud fragmented. Not everywhere at once, not uniformly. The metal enrichment was patchy, mixed unevenly through the intergalactic medium by the asymmetric expansion of supernova ejecta and the complex gas dynamics of the mini-halos. Regions that received more enrichment crossed the critical threshold sooner. Regions far from the first supernovae remained pristine longer, continuing to form a population 3 stars while their neighbours had already shifted to something different. But in the regions where the threshold was crossed, the shift was permanent. Once a gas cloud has been enriched above the critical metallicity, it does not unenrich. The metals do not disappear. They remain, available to every subsequent collapse that samples that gas, ensuring that every star forming from it inherits the changed cooling physics and the lower Jeans mass. The transition from massive to small was not reversible in any region where it occurred. The gas that had been making monsters was making something else now. Quietly, in the enriched pockets of the early universe, the first stars of a different character were forming, lower in mass, longer in life, carrying within themselves the chemical inheritance of the objects that came before them. Something had shifted, the same gas in a different state producing a different universe. The gas cloud that forms a star does not know what kind of star it is making. It has no preference, no orientation toward a particular outcome. It collapses because gravity exceeds pressure, fragments or fails to fragment based on the relationship between its temperature and the Jeans mass at each stage of the infall, and produces whatever the thermodynamics allow at the density and temperature where the collapse stalls and a protostellar core forms. The star that results is not chosen. It is the output of conditions, which is why the conditions matter so much, and why the arrival of carbon and oxygen in a collapsing gas cloud, even in quantities that a chemist would describe as trace contamination, change the output so completely. Carbon radiates efficiently at low temperatures through a mechanism that hydrogen and helium cannot use at those conditions. The ionized carbon fine structure line at 158 microns, a transition between two very closely spaced energy levels in the ground state of the carbon ion, can be excited by thermal collisions at temperatures below 100 Kelvin, temperatures where molecular hydrogen has already reached its cooling floor and stopped contributing meaningfully to the energy balance of the gas. This is the key difference, and it is structural rather than incidental. The energy spacing of the carbon transition is small enough that collisions at low temperatures carry sufficient energy to trigger it, while the transitions available to molecular hydrogen require more energetic collisions and are therefore suppressed below the 200 Kelvin floor. Oxygen contributes similarly, through its own fine structure transitions at 63 and 146 microns, effective at temperatures that would leave hydrogen-only gas stuck at its floor. Together, carbon and oxygen in even trace abundances, the 10 to the minus 5 solar metallicity threshold discussed in the previous chapter, an amount almost vanishingly small against the background hydrogen and helium, provided a continuous cooling ladder that extended downward past 200 Kelvin, past 100, past 50, into the temperature ranges that primordial gas never reached. At the bottom of that ladder is something around 10 Kelvin. 10 Kelvin is, and I find myself wanting to sit with this number for a moment because it resists ordinary reference. 10 Kelvin is 263 degrees below zero in Celsius. It is colder than the surface of Pluto. It is a temperature at which nitrogen gas liquefies, at which most molecular reactions slow to rates that are practically zero, at which the thermal motion of gas particles has been reduced to something close to the minimum that quantum mechanics permits for a system at finite temperature. That gas clouds in the present-day galaxy routinely reach this temperature in their coldest cores feels, when you actually think about the number, slightly improbable. But they do. The cooling physics of metal-enriched gas is efficient enough to get there, and at 10 Kelvin, the Jeans mass in a collapsing cloud core is not hundreds of solar masses. It is not tens. It is closer to 1 solar mass, the scale at which an object can become gravitationally independent and begin its own inward collapse, separate from the larger cloud, destined for something small and long-lived. This is what the presence of carbon and oxygen in a gas cloud actually produced. Not directly, not immediately. The cooling to 10 Kelvin happened over the course of the gravitational infall as the cloud contracted and the gas density rose. And the transition to solar mass fragmentation was not instantaneous, but a gradual shift in what scale of substructure could become self-gravitating. But the direction was clear and the outcome was new. Somewhere in the early universe, in a gas cloud that had been enriched above the critical metallicity by the ejector of a population 3 supernova, a clump of gas with roughly 1 solar mass of material became gravitationally unstable and began to collapse on its own. The first solar mass protostar, not announced, not marked, just a slightly denser region of an already collapsing cloud finding itself past the gene's threshold at the right scale, at the right temperature, and beginning to fall inward. What that object eventually became, whether it ignited hydrogen fusion, whether it survived its formation environment, whether it is still burning somewhere in the Milky Way today, we cannot know. The first solar mass stars would have formed from gas enriched by the first population 3 supernovae, which places them very early in cosmic history, in an epoch where individual objects are beyond the reach of current observation. But the physics that produced them is understood, and the transition it represented was real. A universe that had previously been constrained to make one kind of thing massive, short-lived, brilliant, and brief, now had access to another kind. Stars that burn slowly. Stars that last billions of years rather than millions. Stars that can, given the right secondary chemistry and the right planetary architecture, host the long, slow processes that complexity requires. The Sun is a star of roughly 1 solar mass. It formed 4.6 billion years ago and will burn for another 5 billion. It is, in terms of what it produces and how long it lasts, exactly the kind of object that became possible when carbon and oxygen reached the gas clouds of the early universe in sufficient trace abundance to push the cooling past the molecular hydrogen floor. None of that was arranged. The carbon arrived because a massive star died explosively. The cooling followed from atomic physics that predates the universe entirely. The gene's mass dropped because temperature and mass are linked by an equation that does not negotiate. But the outcome, the slow steady stars, the long timescales, the eventual possibility of everything that long timescales allow, was downstream from the moment a gas cloud received enough carbon and oxygen to cool past 200 Kelvin for the first time. Something unwound, quietly, and the universe it left behind was one with more room in it than before. Dust, in the astronomical sense, is not what the word suggests. It is not the fine grey powder that settles on surfaces in a room. It is solid particles, tiny irregular grains of carbon compounds, silicates and oxides, ranging in size from a few nanometers to perhaps a few microns, suspended in the gas of the interstellar medium, produced wherever the right elements exist in sufficient concentration and the right conditions allow them to condense into solid form. In the present-day galaxy, dust is everywhere. It reddens starlight, dims background objects, accumulates in the cold, dense cores of molecular clouds, where it does the cooling work that eventually produces planets. You cannot look at an image of a star-forming region without seeing its effects. The dark lanes in the Orion Nebula, the opaque pillars in Carina, the dense filaments in Perseus where new stars are currently assembling inside cocoons of gas and grain. Dust is so thoroughly woven into present-day star formation that it is easy to treat it as a given, a background condition, something that was always there. It wasn't. Before the first population 3 supernovae, there was no dust anywhere in the universe. Dust requires elements heavier than helium to form, and the only source of those elements in the early universe was stellar nucleosynthesis, the fusion chains inside massive stars and the explosive events that disperse their products. The first dust was made in the cooling ejector of the first supernova, where silicon and carbon and oxygen atoms newly liberated from the stellar interior found themselves in gas that was expanding and cooling rapidly enough for solid phase condensation to occur. The grains that formed were small, a few nanometers across in many cases, irregular, mixed in composition, some carbonaceous, some silicate, some oxide, swept outward with the rest of the supernova ejector into the surrounding gas, eventually mixed by turbulence and the dynamics of the expanding remnant into the interstellar medium of the early universe alongside the gas phase metals already discussed. What these grains could do once they arrived in a collapsing gas cloud was different in character from what carbon and oxygen fine structure lines did. Metal line cooling operates at relatively low densities, where the gas is still diffuse enough that photons carrying the cooling radiation can escape the cloud freely. But at higher densities, the cloud becomes optically thick, photons are reabsorbed before they can carry energy away, and the gas phase cooling channels become less effective. This is where dust took over. At densities above roughly 10 to the 10th power particles per cubic centimetre, densities reached in the inner regions of a collapsing protostellar core, dust grains became the dominant energy transfer mechanism. The process is not radiative in the same way. Gas particles colliding with a dust grain transferred kinetic energy to the grain directly, heating the grain, which then radiated that energy away as thermal emission in the infrared. The grain acted as an intermediary, absorbing thermal energy from the gas through collisions and re-emitting it as radiation that could escape the cloud at wavelengths where the opacity was lower. A radiator pressed against a warm wall and drawing the warmth away through contact rather than convection. Slow, continuous, dependent on surface area and temperature difference rather than photon escape. Dust cooling in dense cloud cores works the same way. The efficiency depends on the total grain surface area available for gas grain contact, which is why small grains are more effective per unit mass than large ones, and why the size distribution of dust matters not only for how it reddens starlight, but for how efficiently it cools collapsing gas. The effect on the gene's mass was significant. Metal line cooling pushed the temperature of collapsing gas down from 200 Kelvin toward 10 Kelvin in the diffuse stages of the infall, bringing the gene's mass from hundreds of solar masses to roughly 1. Dust cooling operating at the higher densities reached in the later stages of protostellar collapse pushed the fragmentation scale down further, to substellar masses, to planetary masses, to the scale at which the solid cores of planets can form within a protoplanetary disk. A few nanometers across, a particle that would be invisible to the naked eye even if you held it directly in front of your face in good light. The entire argument about planetary systems being a natural downstream product of star formation, rather than a rare or special condition requiring unusual circumstances, hinges on particles this size being present in collapsing gas clouds in sufficient abundance to do this specific thing at high densities. The disproportion is real, and I'm not sure what to make of it except to note it and continue. What dust cooling produced, over the billions of years that followed the first supernovae, was a star formation process in which the collapse of a gas cloud naturally generated not only a central star, but a disk of material around it, a protoplanetary disk, in which the same dust grains that had enabled the cooling were now present in large enough concentrations to begin sticking together. Coagulation, pebbles forming from grains, planetesimals from pebbles, rocky cores from planetesimals. The sequence from interstellar dust grain to rocky planet surface is long and complicated, and involves physics well beyond the scope of this chapter, but the starting point is the grain, and the grain started with the first supernova. The ground beneath you, the soil, the rock, the silicate mantle, the iron core, is downstream from the dust that condensed in the ejecta of population 3 stars that died before the sun had any right to exist. Hold that handful of soil long enough to feel the individual grains pressing against your palm. Some of the atoms in it travelled a very long way to get there. Not every population 3 star ended in an explosion. The ones between roughly 40 and 140 solar masses, and those above approximately 260 solar masses, did not produce pair instability supernovae or successful core collapse events. They collapsed. The core contracted past the neutron star density threshold, past any pressure support that nuclear matter could provide, and continued inward until the gravitational field became strong enough to prevent any signal, light, radiation, any physical influence, from escaping. A black hole formed at the location of the star, carrying inward the mass of the object that had existed there, without an outward explosion to announce the transition. The star was there. then it was not there in the way stars are there. Something else was in the same location, with the same mass, doing nothing visible. For stars above 260 solar masses, the upper range of the population 3 distribution, the remnant black holes were not small. An object of 300 solar masses collapsing directly to a black hole produces a black hole of roughly comparable mass, reduced somewhat by the energy carried away in neutrinos during the collapse, but not dramatically. These were intermediate mass black holes, objects in the range of perhaps 100 to 1000 solar masses, sitting in the centers of their dark matter, mini-halos, after the stellar material had vanished, accreting whatever gas remained in the surrounding environment. And here is where the timescale becomes the thing that matters. The universe, at the epoch when these first black holes formed, was less than 300 million years old. The black holes had the remainder of cosmic history ahead of them, billions of years in which to accrete gas, merge with other black holes as their host minihalos merged into larger structures, grow through the hierarchical assembly of cosmic structure that built small halos into large ones, small galaxies into large ones, over the 13+ billion years between then and now. Growth through accretion is limited, at any given moment, by the Eddington rate, the maximum accretion rate at which the radiation pressure from the infalling, heated gas does not push the gas away faster than gravity pulls it in. Sustained Eddington rate accretion causes a black hole mass to increase exponentially, doubling on a timescale called the salpeter time, roughly 45 million years. Starting from a seed of a few hundred solar masses and accreting at the Eddington rate continuously, black hole could reach 1 billion solar masses in something like 1 billion years. Just barely. And this is where the problem lives. And I want to be clear that this is a genuine, unresolved problem in observational cosmology, not a gap to be dismissed. Because the observations show that billion solar mass black holes existed when the universe was less than 1 billion years old. The quasars detected at redshifts above 6, objects whose light left them when the universe was under 1 billion years old, are powered by accretion onto black holes of this scale. 1 billion solar masses assembled in less than 1 billion years. The salpeter timescale calculation, worked backwards from those observed masses to find what seed mass would have been required, produces an uncomfortable answer if you start from the stellar mass black holes that standard supernova remnants produce, objects of 10 to 50 solar masses. The growth from 10 solar masses to 1 billion solar masses at Eddington rate accretion requires more time than was available, not by a small margin, by a significant one, even under optimistic assumptions about accretion efficiency and continuity. The time scale is the problem, not the physics of accretion, which is well understood. The time available between the first stars and the first observed quasars is simply not long enough to grow a stellar mass seed into 1 billion solar masses if accretion proceeds at realistic rates with realistic interruptions. An intermediate mass seed, something in the hundreds to thousands of solar masses formed by the direct collapse of a population 3 star above 260 solar masses, changes the calculation. Starting from 500 solar masses rather than 10 solar masses by several e-folding times of growth, combined with the possibility of mergers as host halos merged, an episodic super-Eddington accretion that some models allow in the dense gas environments of early mini-halos, the gap between seed and billion solar mass quasar becomes, if not comfortable, at least physically plausible within the available time. This is still a proposal, not a confirmed pathway. The origin of supermassive black holes is one of the genuinely open questions in modern astrophysics, and the direct collapse of population 3 stars is one of several mechanisms under active investigation, alongside direct collapse of primordial gas clouds without a stellar phase, and runaway stellar mergers in dense early star clusters. The evidence does not yet definitively favour any single pathway, but the seed is real. The intermediate mass black holes left by the most massive population 3 stars existed, formed early, and had time on their side in a way that no later forming seed did. The Milky Way has a supermassive black hole at its centre, Sagittarius. A star, as it is designated, has a mass of approximately 4 million solar masses. It sits at the centre of the galaxy, surrounded by a dense cluster of stars doing nothing dramatic at the moment, accreting at a very low rate, quiet by quasar standards, detectable primarily through the orbits of stars moving around it at speeds that only that much mass in that smaller volume can explain. There is a reasonable possibility, not certainty, but a reasonable possibility, that it grew from a seed that was once a star. A population 3 star above 260 solar masses, forming in a dark matter mini-halo in the first few 100 million years of the universe's existence, collapsing without explosion into a black hole that then accreted and merged its way through 13 billion years of cosmic assembly to become the object whose gravitational influence we now measure through stellar orbits at the centre of our own galaxy. Standing at the base of something whose top you cannot see, the ground feeling more solid than usual, the scale registered not through sight but through the angle at which everything else arranges itself around it. Whatever is at the centre of every large galaxy has a history, and part of that history may be a star that no longer exists, in a Minihalo that no longer exists as a separate structure, in an epoch of the universe that left almost no direct evidence of itself behind. Almost. There are stars in the outer halo of the Milky Way that formed before the Sun by several billion years, in gas clouds that have been touched by only 1 or 2 population 3 supernovae, and that have been burning quietly ever since. Low-mass stars, well under a solar mass, with lifetimes long enough to survive to the present day, carrying in their surface layers the chemical composition of the gas from which they formed. They did not make the elements in their atmospheres, they inherited them. And because these stars are old enough and their interiors cool enough that the surface composition has not been significantly altered by internal mixing or nucleosynthesis, the abundances you measure in their photospheres today are, to a reasonable approximation, the abundances of the gas cloud that collapsed to form them, which means they are, to a reasonable approximation, the yields of whatever supernovae enriched that gas. The field built around this idea, using the surface abundances of extremely metal-poor stars to reconstruct the properties of their POP3 progenitors, is called stellar archaeology. It proceeds through spectroscopy, taking the light from one of these ancient stars, splitting it into its component wavelengths, and reading the absorption lines produced by the different elements present in the stellar atmosphere. Each element leaves its signature at specific wavelengths. The depth of the line encodes the abundance. A spectrum of sufficient resolution and signal-to-noise ratio can tell you, with quantifiable uncertainty, the relative concentrations of carbon, oxygen, magnesium, calcium, iron, and dozens of other elements in the atmosphere of a star that formed billions of years ago from gas enriched by stars that formed before it. The stars that matter most for this work are the ones with the lowest iron abundances. Iron is used as a proxy for overall metal content, not because it is the most abundant heavy element, but because its spectral lines are numerous and well characterized and measurable even in very metal-poor stars. The notation used to describe iron abundance is Fe/H, defined as the logarithm of the iron-to-hydrogen ratio in the star relative to the same ratio in the Sun. A star with Fe/H equals -2 has 1/100th of the Sun's iron abundance. Fe/H equals -4 is 1/10,000th. Fe/H equals -5 is 100,000th. The most iron-poor stars known have Fe/H values around -6 or lower, 100 millionth of the Sun's iron content. These numbers look like notation, and I think that sometimes the notation gets in the way of what it means. A star with Fe/H equals -6, formed from gas that had been touched by so little stellar processing, so few prior supernovae, that the iron content is essentially a rounding error against the hydrogen background. These are objects sitting at the very edge of the POP3 to POP2 transition, their composition reflecting the earliest stages of chemical enrichment in the history of the galaxy. Among these extremely metal-poor stars, a particular subclass stands out. Carbon-enhanced metal-poor stars, designated CEMP stars in the literature, show carbon abundances elevated far above what their iron content would predict if they had formed from gas, enriched by the same processes that dominate present-day nuclear synthesis. The ratio of carbon to iron in CEMP stars is sometimes 100 times higher than in the Sun, sometimes more. Their oxygen and nitrogen abundances tell a similar story of enrichment by something that produced carbon and lighter elements efficiently but relatively little iron. This pattern matches, reasonably well, the predicted nucleosynthetic yields of POP3 stars in certain mass ranges, particularly the rotating massive stars and the lower mass POP3 supernovae that produced yields weighted towards the lighter elements. The CEMP abundance pattern is not perfectly explained by any single POP3 progenitor model, and there is ongoing discussion about what range of progenitors and explosion energies best reproduces the observed spread in CEMP compositions. The match is not exact, but it is close enough and systematic enough that the mainstream interpretation treats CEMP stars as the most likely direct chemical descendants of the first stellar generation. There is something I find difficult to move past quickly here, and I want to name it plainly rather than dress it up. These stars are in our galaxy, not at cosmological distances, not accessible only through the light travel time from redshift 10 or 15. In the Milky Way halo, at distances of a few thousand to a few tens of thousands of light years. Some of them have been studied in enough spectroscopic detail that their individual elemental abundances are known to better than 0.1 Dex precision. The evidence for the first stars, for the objects that made the first metals, that seeded reionization, that left the chemical fingerprints we have been following through this entire story, is sitting in our own galactic backyard, in stars that have been burning quietly for over 10 billion years. While the sun formed and the earth formed, and everything that followed unfolded around them. Reading very old handwriting, not for what it says at first, but for the physical fact of the ink on the page, the marks made by a hand that no longer exists, the strange and slightly disorienting proximity the document creates between you and something that happened long before you. This is roughly what it feels like to read a spectrum of a Vis star with Fe/H equals -5.5. The data is being collected now. The telescope is operating now. The photons hitting the detector left a star that is several thousand light years away and 12 billion years old. The absorption lines in the spectrum were set when that star formed, in a gas cloud enriched by a supernova that occurred before the Milky Way had assembled into anything resembling its current form. That's not a metaphor for something. That's what's actually happening when an astronomer reduces a high-resolution spectrum of an extremely metal-poor halo star on a Tuesday afternoon. The first stars are gone. They burned for 2 or 3 million years and then ended, violently or silently depending on their mass, and the objects themselves do not exist. But what they put into the gas is still there, still measurable, preserved in the atmospheres of stars that formed just after them, and have been coasting on that inheritance ever since. We didn't have to go far to find it. For most of the history of this field, population 3 stars existed only in theory, and in the chemical record they left in a metal-poor halo stars. The objects themselves are the actual stellar sources, burning at 100,000 Kelvin in the first mini-halos of the early universe, were too distant, too faint, and too brief to detect with any instrument available before the James Webb Space Telescope began operations. The theory was solid. The indirect evidence from stellar archaeology was consistent, but direct observation of POP3 stellar signatures, or of objects whose properties match the theoretical predictions closely enough to constitute a detection, remained out of reach. JWST changed the reach, not the difficulty, the reach. The telescope is optimized for infrared observations, which matters for high redshift science in a specific way. Light emitted by objects at redshifts of 6, 8, 10 or higher has been stretched by the expansion of the universe. Photons that left those objects as ultraviolet radiation arrive at Earth as infrared, shifted by a factor of 1 plus Z. A photon emitted at 120 nanometers ultraviolet by a source at redshift 10 arrives at a wavelength of roughly 1.3 microns, comfortably within the near-infrared range, where JWST's NIR spec and NIR cam instruments operate with sensitivity that no previous space telescope approached. The early universe's ultraviolet light is accessible to JWST precisely because of the expansion that makes it seem so remote. The signatures astronomers search for in a potential POP3 source are specific, and their specificity is what makes them useful. The most important is the HE2 emission line at 1,640 angstroms in the rest frame, produced when doubly ionized helium recombines and drops from the third to the second energy level, releasing a photon at this wavelength. To doubly ionize helium, to strip both electrons from a helium atom, a photon must carry at least 54.4 electron volts of energy. This is not a minor threshold. The ionization energy of hydrogen is 13.6 electron volts, which is already sufficient to limit the stellar sources capable of driving significant hydrogen ionization. The energy required to doubly ionize helium is 4 times that. The list of astrophysical sources that produce photons above 54.4 electron volts in numbers large enough to generate detectable HE2 emission in the surrounding gas is short, and population 3 stars, with their surface temperatures near 100,000 Kelvin, placing the peak of their emission in the extreme ultraviolet, sit near the top of it. The presence of HE2 emission in a source, combined with the absence of metal emission lines, is the cleanest available signature. Metal lines, oxygen forbidden lines, carbon lines, nitrogen lines are produced in gas that has been enriched, and their absence in a spectrum alongside strong HE2 emission is what you would expect from a system of pristine metal-free stars ionizing pristine, metal-free surrounding gas. Every alternative explanation for strong HE2 emission, active galactic nuclei, Wolf-Rayet stars, X-ray binaries, tends to produce associated metal features in the spectrum or requires conditions that conflict with other observed properties of the source. The absence of metal lines is not proof, but it is a constraint. In 2024, Maiolino and colleagues reported observations of a faint companion object, subsequently referred to as Hebe, located approximately 3 kiloparsecs from the galaxy GN-Z11, one of the brightest known galaxies in the early universe, at a redshift of approximately 10.6. The source was detected using NIR spec YFU, JWST's near-infrared integral field spectrograph, which can obtain spatially resolved spectra across a small region of sky simultaneously. Hebe showed emission at the expected wavelength of HE2, 1,640 angstroms, redshifted to the infrared as expected for a source at Z equals 10.6. Associated metal emission lines were not detected. The interpretation offered was that Hebe might represent a cluster of population 3 stars in a metal-free region of gas adjacent to the already enriched GN-Z11. Its HE2 emission, driven by the extreme ultraviolet output of pristine massive stars ionizing surrounding pristine gas. The interpretation is plausible. It is not confirmed. Alternative explanations involving AGN activity or unusual stellar populations in a low metallicity but not metal-free environment remain technically consistent with the delta, and the community's response has been appropriately cautious about claiming a detection on the basis of one object with limited signal-to-noise in the relevant line. A strong HE2 emitter at redshift 8.16, designated RxJ2129-Z8HE2, represents a separate candidate identified through different survey data. A third candidate, LAP1-B at redshift 6.6, was identified by Nakajima and colleagues in 2025, using gravitational lensing by the foreground cluster MACSJ0416, which amplified the source's light sufficiently to allow spectroscopic characterization. LAP1-b was described in subsequent analysis as the first object to satisfy simultaneously 3 independent theoretical predictions for POP3 star formation. Formation in a halo with virial temperature in the range expected for molecular hydrogen cooling, a top-heavy stellar mass distribution inferred from the ionizing photon budget, and a total stellar mass in massive stars consistent with the cluster masses that fragmentation and feedback models predict. 3 predictions, 1 object, tentatively consistent. I want to be careful about what that means. Consistent with is not the same as confirmed as. The signal-to-noise of the observations, the modelling assumptions required to translate observed line ratios into inferred stellar populations, the alternative explanations that cannot yet be fully excluded, all of these leave the status of LAP1-b, and of the other candidates, as something that the field would describe as promising rather than established. But promising is different from where things stood 5 years ago. Shapes are present in the low light that were not present before. The adjustment is taking longer than the most optimistic predictions suggested it would. The signatures are real. The candidates are real. The gap between candidate and confirmed detection is also real, and it is the gap that the next generation of observations, deeper spectroscopy, better signal-to-noise independent confirmation, is designed to close. Something is there. The spectrum suggests it. The theory predicts it. And the instruments are, for the first time, sensitive enough that the answer is no longer definitely out of reach. The earliest serious numerical simulations of population 3-star formation, produced in the early 2000s by Abel, Brian, Norman, and separately by Brom, Copier and Larson, arrived at a result that was clean and in retrospect perhaps too clean. 1 massive star per mini-halo. A single dominant object forming at the centre of the collapsing primordial cloud, accreting the available gas without competition, reaching masses of hundreds of solar masses before feedback terminated the growth. The picture was compelling partly because it was legible, 1 object, 1 outcome, the physics pointing in a single direction toward a single result. That picture has been substantially complicated since, not discarded. Complicated. The first major revision came from higher resolution simulations that followed the collapse further into the protostellar phase, past the point where the earlier work had stopped. When you resolve the accretion disk that forms around the central protostar, the rotating structure of gas that builds up as in falling material with angular momentum cannot fall straight in, you find that the disk is unstable. It fragments. Not into the hundreds of pieces that a present-day molecular cloud produces, not into a distributed population of solar mass objects, but into a small number of secondary condensations, 2 or 3 or occasionally 4, each capable of becoming a separate protostar and accreting its own share of the available gas. This is disk fragmentation, and it is now understood to be a common outcome of primordial star formation rather than an exception. The disk becomes gravitationally unstable when the ratio of its mass to the mass of the central object exceeds a threshold, and the high accretion rates in primordial gas, the same high rates that drove the formation of massive protostars, also drove the disk mass up quickly enough to trigger this instability in many simulations. The result was that 1 star per halo became a small multiple system per halo in most modern treatments. The total mass assembled in the halo did not change dramatically. What changed was how that mass was distributed among the objects that formed from it. Turbulence added another layer of complication. The classical picture assumed relatively smooth primordial gas falling into the mini-halo without significant turbulent structure. More recent work, including simulations published in 2024 and 2025, has shown that turbulence in primordial mini-halos, driven by the streaming motions between baryons and dark matter that are a natural consequence of the epoch of recombination, could produce significant clumping in the star-forming gas before the central collapse was complete. Some of these clumps, in the simulations, had masses in the range of 2 to 70 solar masses. Not the hundreds that the smooth collapse models predicted as characteristic, not 1 solar mass, but significantly lower than the upper end of the classical expectation, and distributed across a wider range. A map drawn from memory. The overall shape correct. Yes. The first stars were overwhelmingly more massive than present-day stars, yes. The physics of H2 cooling and hygiene's masses still applies. Yes, the population was top-heavy in a way that no present-day stellar population is. But certain details off. The minimum mass lower than the early models suggested. The number of objects per halo higher. The uniformity of the population too. All hundreds of solar masses, all isolated giants, replaced by something messier. A distribution with a tail extending towards smaller objects alongside the dominant massive ones. Magnetic fields complicated things further still. When magneto-hydrodynamic effects were included in simulations, and primordial gas likely carried some cosmological magnetic field, amplified by dynamo processes during the collapse, the results shifted again. Magnetic pressure resisted disk fragmentation, tending to stabilize the accretion disk against the instabilities that produced secondary condensations in purely hydrodynamic runs. In the MHD simulations, the maximum stellar mass dropped, some runs producing primaries of only 60 solar masses rather than several hundred. But the number of companions also dropped, the system tending back toward fewer, less massive objects rather than the multiple star clusters that turbulence-inclusive models sometimes produced. The honest summary is that the simulations do not yet converge. Different groups, using different codes, different resolutions, different treatments of the relevant physics, get different answers for the POP3 IMF. The uncertainties are genuine and not trivial. This is what progress in this field often looks like up close, not a clean new picture replacing a clean old one, but a set of partial results pointing in partially consistent directions, the truth somewhere in the overlap of their constraints. What they all agree on is worth stating plainly. Even the lowest mass objects produced in the most turbulence-inclusive, fragmentation-heavy simulations are still several solar masses. The minimum end of the revised POP3 mass range is not one solar mass. It is not the present-day stellar mass function. The physics of H2 cooling and the high Jeans mass of primordial gas still operated, still set a floor well above what present-day molecular clouds produce, still ensured that whatever form was large by modern standards. The first stars were not a monolith of identical giants. They were probably a population, broader than the early models suggested, including companions and smaller siblings alongside the most massive objects. But even the smaller siblings were not small. The map was mostly right. Some of the details were off. Navigating by it would still get you somewhere close to where you needed to go. The conditions that produced the first stars were not exotic. They did not require unusual physics or rare configurations of matter, or some special initial state that the universe was unlikely to have reached. They required only three things: gas of primordial composition, dark matter mini-halos providing gravitational wells deep enough to concentrate that gas, and the absence of any prior stellar activity to have altered either. These three things coexisted for a specific window of time. That window closed. And the reason it closed is not that the universe ran out of hydrogen, or that dark matter mini-halos stopped forming, or that some external process intervened. The reason is that the first stars themselves closed it. By existing, by burning, by dying the way they died, Population 3 stars systematically dismantled every condition that had made them possible. The metal enrichment came first in the sense of being the most direct. Each pair instability supernova ejected roughly 100 solar masses of heavy elements into the surrounding gas. The ejector expanded outward, mixed with the intergalactic medium, shred through the mini-halos and the space between them on timescales of millions to tens of millions of years. The critical metallicity threshold, that vanishingly small contamination of 10 to the power of -5 solar metallicity, was crossed in the regions nearest to the first supernova relatively quickly on cosmic timescales. Once crossed, it stayed crossed. The metals do not decay. They do not separate back out of the gas. They remain in the interstellar and intergalactic medium, available to every subsequent collapse, permanently lowering the gene's mass in every enriched region and permanently precluding the formation of truly pristine stars in those volumes. A gas cloud that has been enriched above the critical metallicity will never again produce population 3 stars. Not because something is preventing it, because the physics that defined population 3 formation, the high gene's mass, the lack of efficient cooling below 200 Kelvin, the undivided infall into one or two massive objects, no longer applies to that gas. The gas has changed. What it produces has changed with it. The ionizing background came alongside the metal enrichment, inseparable from it in practice. Population 3 stars poured ultraviolet radiation into the intergalactic medium throughout their lifetimes. As more stars formed and more radiation accumulated, the background ultraviolet field in the early universe grew. This radiation had a specific effect on the molecular hydrogen in Minihalos that had not yet formed stars. It dissociated H2. Photons in the Lyman-Werner energy band between 11.2 and the 13.6 electron volts, able to penetrate neutral gas more easily than photons above the hydrogen ionization threshold, were absorbed by H2 molecules and broke them apart into atomic hydrogen. Molecular hydrogen was the only cooling agent available to pristine primordial gas. Remove it, and the gas in a mini-halo cannot cool efficiently enough to collapse to stellar densities. The Lyman-Werner background produced by the first generation of stars therefore suppressed star formation in neighbouring mini-halos that had not yet formed their own stars, raising the minimum halo mass required for star formation and extending the period before those regions could produce anything. In the most exposed regions, star formation was delayed significantly. In some small halos, it may have been prevented entirely. The universe, in other words, was not uniformly ready to form stars at all times after the first ones ignited. The first stars made parts of it less ready, not more, at least temporarily, at least locally. But temporary was long enough. By the time the Lyman-Werner background was established across significant volumes of the early universe, the metal enrichment from the first supernova had also begun spreading, and the combination of these two effects, reduced H2 in some regions, increased metallicity in others, was already shifting the character of star formation away from the primordial mode, not everywhere at once, not in any coordinated way, but the direction was set. The temperature floor of the intergalactic medium also rose and stayed risen as ionization progressed. The photoheating of the intergalactic medium by the cumulative ultraviolet output of stars and early galaxies raised the temperature of the diffuse gas between galaxies to tens of thousands of Kelvin, temperatures at which the gas cannot cool and collapse into the smallest mini-halos. The minimum halo mass for star formation increased. The smallest structures, the 10 to the power of 5 to 10 to the power of 6 solar mass mini-halos, where population 3 stars had formed, were no longer sites where gas could efficiently accumulate and cool. The universe had graduated in some sense past the mini-halo epoch. None of this is, and I want to be careful about this, none of this is what we typically mean when we say something was lost. The closure of POP3 formation conditions was not a subtraction from the universe's capabilities. It was a consequence of those capabilities operating. The first stars enriched the gas, ionized the background, raised the temperature floor, because that is what burning hydrogen in stellar cores and dying in supernovae does to the surrounding medium. Many physical processes alter the conditions that produce them. This one happened to do it at cosmological scale. What resulted was a universe that was irreversibly more complex than the one the first stars were born into, and permanently incapable of returning to the state that had produced them. The pristine gas is gone, not rare. Gone, replaced, enriched, heated, altered in every volume of space that has been reached by the light and the ejector of every star that has ever burned. The conditions for population 3 formation exist now only in theory, in the equations that describe what those conditions were, not in any actual region of the present universe. Something that happened once cannot happen again. Not because the physics changed, because the physics the first time changed everything else. There was a time, brief by the standards of what followed but real, and long by any human measure, when the universe had no heavy elements anywhere, no carbon moving through the interstellar medium, no oxygen in any molecular cloud, no silicon in any planetary body because there were no planetary bodies, no iron. The periodic table existed as physics, as nuclear possibility, but not yet as inventory. The universe was running on 2 elements and a footnote, and everything it would eventually become was waiting inside the equations, not yet extracted. The first stars extracted it, not deliberately, not through any process that resembles intention, but through the straightforward operation of gravity and nuclear physics across 2 to 3 million years per star, repeated in mini-halo after mini-halo across the early universe, each star burning through its hydrogen supply and dying in the way its mass dictated and releasing into the surrounding gas whatever its interior had built. The extraction was real, the elements were real, and the universe that existed after the first generation of stars had lived and died was different, in specific measurable chemical ways, from the universe that had existed before them. What that difference eventually became is what this chapter is about. The oxygen in the air you are breathing right now, this specific breath, the one currently expanding the lungs, the one that will be exhaled in a few seconds and replaced, was produced inside a massive star. Not a population 3 star necessarily. The oxygen in Earth's atmosphere has a complicated nucleosynthetic history that includes contributions from many stellar generations across many billions of years. But the chain begins with the first stars. The first free oxygen anywhere in the universe came from pair instability supernovae in the early universe, and every subsequent oxygen atom was produced by a process that those first explosions made possible by seeding the interstellar medium with the chemical conditions that allowed the next stellar generation to form and evolve differently. The chain is real. It does not need additional meaning attached to it. It is simply the causal sequence. No pop 3 stars, no first metals, no critical metallicity transition, no efficient cooling below 200 Kelvin, no solar mass star formation, no sun, no earth, no oxygen-nitrogen atmosphere, no breath. Each link is documented. The chain holds. The calcium in bone came the same way. The iron circulating in blood, iron, which is the endpoint of silicon burning in massive stellar cores, the element at which nuclear fusion stops releasing energy, the element that accumulates in stellar cores until they collapse, arrived in the interstellar medium through supernovae of various generations, tracing back through the chemical evolution of the galaxy to the first heavy elements produced by the first stars, the silicon in the ground, in the rock, in the sand, the carbon in every organic molecule and every living thing. These are not poetic connections, they are physical ones, traceable through nucleosynthesis models and abundance measurements and the chemical evolution of the galaxy across 13 billion years. The body you inhabit is made of elements that did not exist before the first massive stars lived and died. Not most of the elements. All of the elements heavier than lithium. Everything that makes biology possible. Everything that makes solid ground possible. Everything that makes the specific chemistry of a living system possible. All of it downstream from stellar nuclear synthesis. All of it absent from the universe before the first stars provided it. The sun exists because of the first stars, not directly, so the sun formed 4.6 billion years ago from a molecular cloud that had been through many cycles of stellar enrichment by then, a cloud enriched with metals from many generations of stars across the history of the galaxy. But the first metals in that lineage, the first carbon and oxygen that allowed gas clouds to cool past 200 Kelvin and fragment into solar mass objects, came from population 3 supernovae. The sun could not have formed from the gas the universe started with. It required enriched gas. The enrichment started with the first generation. The supermassive black hole at the centre of the Milky Way, Sagittarius. A star, 4 million solar masses, sitting quiet at the galactic centre, may carry in its mass the remnant of a population 3 star that collapsed directly to a black hole in the first few 100 million years of the universe's existence, and then grew, through accretion and mergers across 13 billion years, into what the stellar orbits at the galactic centre now trace. May. The origin of supermassive black holes is not settled, but the possibility is real, and the timescale is right, and the mass is the right order of magnitude for what direct collapse from a POP3 progenitor could eventually produce. The transparency of the universe, the fact that light can travel billions of light years through the intergalactic medium without being absorbed by neutral hydrogen gas, the fact that we can see galaxies at redshift 10 and quasars at redshift 7, and the cosmic microwave background at the edge of the observable universe. This transparency was produced by Ionization, and Ionization was started by population 3 stars. The universe we observe in every direction through every telescope is observable because the first stars ionize the gas that would otherwise have made it opaque. If you found this video worthwhile and would like to help the Sleepy Physicist keep going, the Patreon link is in the description. The first stars lived for 2 to 3 million years. They have been gone for over 13 billion. Nothing remains of them directly. No intact stellar remnants, no observable surfaces, no spectra we can point a telescope at and say with certainty that one, that is a population 3 star still burning. What remains is everything else. The elements, the black hole seeds, the transparency, the cooling physics that allowed the second generation to form, the chemical fingerprints in the atmospheres of ancient halo stars, the tentative spectroscopic signatures that JWST is only now beginning to approach, the weight of your hand resting on a surface, the atoms in it pressing against the atoms below, both sets of atoms made in stars, travelling through billions of years of cosmic chemistry to arrive at this particular contact, in this particular moment, in a universe that is transparent enough to see across and complex enough to ask questions in. That complexity has a source. It burned fast, it died completely, and it left everything.